Cool. So, welcome to the RQI Circuit 2026. This is the last local edition of the series of 9 local conferences that we had every single Friday, starting on May 29th, I think, in Stockholm. And we're here in Hanover, at Leibniz University Hannover today. And, well, let's thank Martin Plávala, the local organizer. Let me give it to him, and he can start the conference. Thank you so much, Martin.
Thank you very much. So I'm very happy to have this conference here in Hanover because we have here varied research that touches quantum information and relativistic physics and relativistic quantum information from all sides, be it entanglement in field theories or investigations of contextuality for foundations in physics and in relativistic quantum physics. Also atom interferometric experiments to test gravity and general relativity, and also quantum information experiments with quantum networks. So we're going to hear a lot about this during the day, and I hope you enjoy the conference and have fun. And with that, I'd like to welcome the first speaker, Henrik Wilming, who is a junior professor recently. No, sorry, you're just a professor. Recently appointed professor at the Leibniz University Hannover, and he's going to tell you more about his research.
Okay. Thank you very much. Yeah, I will stay in the light cone here. Thank you. Yes, thanks a lot for the invitation. So I'm Henrik Wilming. As Martin said, I just started a small group, and we work on quantum information and computation. In particular in systems with infinitely many degrees of freedom. And today I will talk about work that's mostly joint work with Laurits van Laek, Alexander Stottmeister, and Reinhard Werner. And we're currently funded by the European Union and the Land Niedersachsen. Okay, so the title is Embezzling Entanglement from Relativistic Quantum Fields. I'll be honest, I will not talk much about relativistic quantum fields. I will mostly talk about embezzling entanglement. And then I will say a little bit about how this might apply to relativistic quantum fields. But I thought I had to make the title fit to the conference. So that's what it is. Okay, so what's the motivation? So we all know that entanglement is very important for physics. And we can think about how entanglement behaves across scales. So let's think about the number of degrees of freedom we have in our system. Then typical quantum information theory works in settings where we have very few degrees of freedom, maybe a couple of spins, maybe 100 spins. Maybe for a quantum computer it goes up to, I don't know, 10,000 qubits or a million qubits, but it's all finite. And here we think of entanglement usually as a resource to perform quantum information processing tasks like, I don't know, teleportation, quantum computation, quantum cryptography, and so on. But in the last decades, it has also been recognized that entanglement is really important as a conceptual tool to understand other things. For example, in many-body physics, it has been extremely influential to understand quantum phases of matter, like topological order, and to devise numerical algorithms like tensor network algorithms. And here it's not so much about using entanglement as a resource, but really using entanglement as a conceptual tool to understand our systems. And then maybe a bit more on the speculative side. Recently, entanglement has also played an important role in studying toy models of quantum gravity, black hole information problem, the holographic correspondence, and so on. And of course, these toy models also work with finite numbers of degrees of freedom, typically. And you can ask what happens if we really go to infinitely many degrees of freedom. How can we understand entanglement from quantum information theory perspective in this regime, where we, for example, have many-body physics and thermodynamic limit, we have genuine quantum field theory, and maybe quantum gravity. Okay, and this is sort of the topic of today's talk. So what is entanglement? I'm from quantum information, so for me, entanglement is what you cannot create by local operations and classical communication. Okay, so we think of typically two agents. They have their local labs, and they can do arbitrary quantum operations on their local labs, and they can also exchange classical messages via a messenger, for example. So how does this look like? Well, we have Alice and Bob. They share some initial state. Here it's just some pure state on each side, which is a bit of a boring situation. But what happens is Alice performs a local measurement. She obtains some outcome with a certain probability. She sends her outcome to Bob. Depending on the outcome, Bob does something to his system, maybe some unitary, performs a measurement, gets another outcome, sends this back to Alice, and then it just goes on until they have some stopping criterion when they know, okay, now we stop our protocol. And this is an LOCC protocol. And we say that a state is more entangled if I can transform this state psi to another state phi with such an LOCC protocol. And here I already concentrate on pure states. This is the simplest case. And you can ask, so the general problem of pure state entanglement theory is, when can I do this? Right? Which state is more entangled than another state? Importantly, this does not say that every two states are comparable. There may be states where none has more entanglement than the other. And this, for finitely many degrees of freedom, this problem has been solved completely in a remarkably nice result by Michael Nielsen in 1999. Therefore, it's called Nielsen's theorem. I will not present you how this goes. It goes through majorization theory. But the important point is that Nielsen's solution only works with finitely many degrees of freedom. So precisely fails in systems like in the thermodynamic limit or for quantum fields. Okay. So this is the background about what is entanglement. And now I would like to give you a brief exposition of some setups where we could think of really going to infinitely many degrees of freedom and why this is interesting. And we'll go through three different settings. So one is quantum information, many-body physics, and quantum field theory. So in quantum information, often it's useful to think of the following question. Suppose Alice and Bob want to achieve something. We can ask how many entangled states do they need to consume to perform their operation up to a given error. And for this, it would be desirable to be able to work in a situation where at first they really we assume they have infinitely many that they share, and we don't care about how many they are, as long as they are finitely many. So what we think of is they have infinitely many, but they always only act on finitely, but possibly unboundedly many. And then we can ask, what can they do? For example, we can compare these two situations. Either they share this state, or they share this state. But now they share infinitely many copies of these two states. Both states are entangled. Doesn't make a difference for them in terms of what they can do. And we'll come back to this question in the end. Any guesses for these two? Okay. Nobody wants to commit, so we'll see in the end. Okay. Another motivation comes from many-body physics. Imagine you have an infinite lattice of spins, and you have a gapped ground state. So you have a ground state, and there's an excitation gap to the first excited states. Then if we look at a finite region with a finite boundary, then typically what's true is that the entanglement entropy fulfills an area law, meaning that the total entropy in this region is bounded by the surface area of this region, and you have a finite amount of entanglement. Now you can make a bipartition where this boundary is infinite. So this area law doesn't seem to tell you anything. Right? You have infinite entanglement, and you can ask, are there different ways of this infinite entanglement in such spin systems? Or are they somehow always the same? Are there different kinds of infinite entanglement? And if so, are there consequences even if I look at a finite system? And finally, the setting of the title. So we can think of Minkowski space-time. Here's a Penrose diagram. And we look at these Rindler wedges. And we imagine, of course we cannot do this, but we imagine that Alice somehow has access to all the observables in this one wedge and Bob to the other. And then it's well known that the vacuum is infinitely entangled. But the question is, what does this mean, this infinite entanglement? Okay. And is it special in some way? Can it do something that another infinitely entangled system cannot do, maybe? And the answer will be yes for this. Okay. So the main takeaways of this talk will be that there are different kinds of infinite entanglement, that they appear in physical models that are sort of reasonable, and they can have consequences for large but finite systems that are hard to detect in the finite system itself. Okay. And the main philosophy will be that if we have an infinite system with infinitely many degrees of freedom, we still want to ask what are the relevant entanglement properties when we always only act on finite but arbitrarily large subsystems. Okay, remember the setting of Alice and Bob. We don't want to allow them to actually at once act on infinitely many spins, but we don't want to put a bound on how many they act on. Okay. And once we do that, we basically have to go away from the textbook approach of bipartite systems. So what is the subsystem in standard textbook quantum mechanics? Well, we have our Hilbert space. It factorizes into a tensor product. Then Alice operators are given by the bounded operators on the first tensor factor and Bob's in the second tensor factor. And of course, the important thing is that these operators commute. Okay. But this is a bit too restrictive. It's not the most general thing we could do for bipartition of a quantum system. Instead, what we will do is we simply say, okay, there's one Hilbert space, there are Alice's operators, and there are Bob's operators, and they have to commute. Okay, we don't require a tensor factorization. Okay. So where do we get this Hilbert space from? Well, typically what we have in mind is that there's some reference state, like the ground state of a many-body system, the vacuum of a QFT, and so on. And we're interested in those states that we can approximate by only acting on finite regions. And from this, we can construct a Hilbert space by a standard construction. So this is the Hilbert space that we talk about. And then where do these sets of operators come from? Well, what we will do is we'll assume that Alice and Bob have access to all operators that can be approximated by local operators in their regions. And this gives us commuting so-called von Neumann algebras acting on the Hilbert space. These von Neumann algebras, their precise definition is not very important for us for the talk. The point is that they will provide an idealized description of what Alice and Bob can do. Because whatever they can do with operators in these algebras, they can approximate by actually acting locally. Okay. And then we'll make some assumptions. So we want that Alice and Bob fully partition the system, and I will come back to this question, what this means. We'll ask that the reference state is pure, and we'll assume a condition which is maybe not familiar to most people, which is called Hague duality. It says that Alice's operators are the commutant of Bob's operators, where the commutant is simply the set of operators that commutes with all of the operators in the algebra. And this implies that these commuting von Neumann algebras are actually what's called factors. That means that there are no non-trivial operators in the algebra that commute with all other operators in the algebra. Okay, so this is a little technical interlude on our assumptions. But the important point is now that if we have an LOCC protocol that maps one pure state in our Hilbert space to another one, to arbitrary precision acting only on finite subsystems here, truly finite, then this is equivalent to the same being possible with operators from the von Neumann algebras. So we can use these von Neumann algebras to analyze the thing that we're really interested in. And that's why we introduce them. And then this will simplify our problem in the end. Okay. So let me come back to this question of these assumptions that I make. So what we have initially is we have some system and we have Alice and Bob, and they must have commuting algebras. Okay. But what we really want is we want to describe a situation where Alice and Bob really have the full system. So they really have a bipartition of the full system. There's nothing left over. Now, in the tensor product framework, there's nothing you have to do this, because the tensor product of the two algebras are the full algebra. But in this more general setup, you have to be very careful about what this means that Alice and Bob describe the full system. So one approach would be what's called tomographic completeness. That means that the global state on the Hilbert space can be uniquely determined from correlation experiments between A and Bob, all possible correlation experiments. And if you have this, then this is equivalent to the statement that the algebras are factors and they generate together the full bounded operators on our Hilbert space. Okay. Another thing you could do, and this is what we did before, if you want, is you can ask that if Alice and Bob, so they're pure states, maybe psi and phi on the Hilbert space, and they induce the same state on Alice's algebra, then there's an important principle in quantum information, which is the uniqueness of purifications, which says that in this case, there's a unitary in Bob's algebra which maps one to the other. Okay. This is really a core principle in quantum information theory. It pops up everywhere. It turns out that this condition is actually equivalent to this Haag duality condition that I mentioned before. Okay. So Haag duality is sort of the Heisenberg picture version of uniqueness of purifications. And now the important point is that these two things are not equivalent. In particular, this does not imply this. So what we will assume in the following is simply both. Okay? We'll be very generous. We just assume that we have tomography, we have factors that generate the full Hilbert space, and we also have Haag duality. And I will come back to the question of what happens if you don't have Haag duality at the very end of the talk, very briefly. Okay. So the last technical thing I have to explain you is that these factors, these von Neumann algebras with trivial center, can be classified. And this is a very important piece in mathematics by von Neumann and Murray, Kohn and Hagerup. And how this goes is that these factors come in three different types, 1, 2, 3. And each has subtypes. So for example, type 1 has countably many subtypes, 1n. And these factors are simply the bounded operators on an n-dimensional Hilbert space. This is sort of what we're used to. Then type 2 comes in two different kinds, called type 1 and type 2 infinity. And type 3 comes with uncountably many different types, indexed by a value lambda in the unit interval. And often one says 1 and 2, they are called semi-finite. They have a trace functional, and 3 is sometimes called purely infinite. They don't have a trace functional, but this is not so important for us right here. Okay, and this situation is clearly what we are used to in ordinary quantum mechanics. So if Alice and Bob have type 1 algebras, this is the tensor product framework you're used to from textbooks. The question is, do these other settings come up? And if so, are they interesting? So let me give you some examples. Here we had the infinitely many copies of this pure state, where now I wrote like a general amplitude here, which we assume to be positive without loss of generality. And again, the Hilbert space that we get is the state that can approximate by acting on finitely many of these spins, on A and B spins. And MA, Alice's algebra, are the operators that can be approximated by acting only on finitely many A spins. And then depending on this lambda, you get different types of this von Neumann algebra. You can get type 1 infinity, type 3 lambda, where lambda is the lambda in our state, type 2 1, and so on. So type 2 1 observed that this is simply having infinitely many maximally entangled states. Okay, let's look at a different example. We have a spin chain. You have a one-dimensional spin chain, and you cut it in the middle. And again, you do the same. You look at the Hilbert space you get from acting with finite operators, and Alice's version of that, of these operators. And then you can ask, okay, what are the possible types that come out? So Matsui has proven that if you have a gapped spin chain, the ground state sector, so meaning you start with a pure ground state and you build this up, yields type 1 factors, so you're in the tensor product framework. But we recently showed that, for example, if you have a critical translation invariant free fermionic chain, any of those, doesn't depend on the details, the ground states always have type 3 1. So type 3 with lambda equal to 1. Okay. So these two, for example, can appear in spin chains. And you can ask, hey, can anything more appear? In spin chains, we don't know. It's an open problem. well, with an asterisk, but I will not go into that. So what about 2D spin systems? It's quite rich. So for example, you can easily construct models in 2D which have a gapped ground state, are translation invariant, are in the what's called the trivial topological phase. It's not important for those who don't know what it is. They fulfill Haack duality, and you get either type 1 infinity, type 2 infinity, or type 3 lambda for any lambda that's non-zero. Okay? This is a tensor network construction, if you wish. So all these different types come up already in 2D gap spin systems. What about relativistic QFT? So, well, let's do a brief reminder of the algebraic formulation. There, if we have some subsets in Minkowski space, we associate phenomenal algebras. Here, this is the vacuum sector. And if you have space-like regions, these commute. And moreover, at least if we have a wedge, and we also want completeness, that if we take the causal completion of a region, we get the same algebra. And if we take wedges like this, at least, we also have Haack duality. That's nice. And it's been a general result that in a relativistic QFT, you always get type 3-1 for these algebras. This is like the critical spin system before. Okay. So now I told you all these things about phenomenon algebras, how they show up in different systems, but what do they have to do with entanglement? And what do these types in particular have to do with entanglement? So it turns out that there's a very close connection between these different types and actual entanglement properties that we can operationally formulate. So to do that, let's talk about some entanglement properties you could have. So for example, we say that a state contains infinite one-shot entanglement if for every finite dimensional pure state, psi, we can transform the state into some other state omega prime on our system tensor psi. That means we can distill out any entangled state that we want. Okay. The question is, do such systems exist? This is clearly a strong way of having infinite entanglement. And the theorem is that this is precisely equivalent under the conditions that we always assume, that MA equivalently MB has type 2 or 3. So this is precisely what you get always if you get outside of the tensor product framework. And if this is the case, if there's one such vector effect, already all vectors have this property. So this is not a property of an individual state, it's a property of the full Hilbert space, if you want. Okay, and we have seen examples of this before, remember, right? In the gap spin systems, we have seen both of these. In QFT, we have seen type 3. In spin chains, we have seen type 3 too. Okay. So the question is, what differentiates type 2 from type 3? Okay. It turns out that at least if your local systems are non-trivial, then if you have type 3, and if and only if you have type 3, all pure states are actually LOCC equivalent. This is a bit crazy because it means that all pure states can be converted into each other via LOCC. They all have the same entanglement. It's just all infinite in the same way, if you wish. This LOCC problem completely trivializes in this setting. And to prove this, we had to generalize this Nielsen's theorem to type 2 and type 3, and then we could make use of some results by Hagrum and Stürmer. Okay. So this is remarkably different from the finite dimensional case. It's different as it could be, basically. In particular, this means that there are no functions that measure entanglement, the amount of entanglement, right? Because the function would have to be constant on the states. And possibly infinite, I guess. Okay, so we have this little table. In type 1, we have finite one-shot entanglement. I didn't present this to you, but it's easy to show. In type 2, we have infinite one-shot entanglement. In type 3, we also have infinite one-shot entanglement, but all states are pure LOCC equivalent. Okay. So what about these different subtypes? Okay. To distinguish those, we first look at maximally entangled state. What's a maximally entangled state? It's different from infinite one-shot entanglement, because here we only ask whether we can convert omega to any other state on the same Hilbert space. Okay? So we say that the state is maximally entangled if omega can be converted into any pure state on the same Hilbert space by LOCC. And you can ask, does such a maximally entangled state exist? And the answer is this. So in type 1n, finite dimensional, yes. Type 1 infinity, no. Type 2 1, yes. Type 2 infinity, no. Type 3, of course, because they're all the same under LOCC. So we can now differentiate in type 2 the subvectors, or the different types, and also in type 1, because type 1n actually has a quantitative version of one-shot entanglement, and type 1 infinity doesn't have a maximum entangled state. Okay, so it remains to ask, what about all these different subtypes here? And now we can come actually to the proper title of the talk, namely embezzlement of entanglement. So what is that? In a fun way, it's the crime of secretly taking entanglement that is in your care or that belongs to an organization that you work for. So what we have in mind is that we have Alice and Bob. They have their local systems, but there's also this safe that they sort of have joint access to. It's in some reference state. And what they want is they want to steal entanglement from the safe. And they want to do this secretly so that nobody can know. So what does this require? Well, once it requires that sort of no record of the crime exists. Okay, so they shouldn't communicate to do this. They shouldn't use classical communication, because then there could be someone intercepting their messages and getting it out. So what they want is only local operations. So what they want is they want to somehow apply local unitaries to their respective subsystem and get out the state that they have and a new state. Why the same state that they have? Because otherwise somebody could find out that the state was changed and see that they stole something. Okay. So let me make an analogy. You might have seen this little trick here where you do this. So you got one piece of chocolate for free. Nice. Well, here it's easy to detect, of course, because there's some stuff you cut out here. But for embezzlement, no such thing can exist. No measurement that can really, with high probability, detect that something was stolen. So we say that we have an embezzling state if we can act on this with a local operation for any error that we want, any epsilon, and get out our original state, tensor, any state that we want. Okay, the important point is that these are the same states. You can ask, yeah?
So this error epsilon that you put there, is this only for the state you take out, or also for the omega, for the initial state? Like, can you just affect the initial state up to epsilon? Are you allowed?
No, you have one state, and then you fix any epsilon that you want and any state that you want, and this is possible.
Yeah, but I'm just asking whether you're allowing for an error epsilon on the first factor of this tensor product,
yes,
or only on the second?
Okay. The global thing. Yeah. And then you can actually find a way to quantify this via sort of best worst case error and worst case error. This is basic quantification of how what's the best vectors for embezzlement and what are the worst. And you see that with this quantification, you actually get a one-to-one correspondence with these type 3 lambda types. So this lambda in type 3 lambda precisely measures how well you can embezzle. This is the message here. And so this reveals what's known as Con's classification of type 3 vectors. I should say that we use Con's result. Okay, this is not like a new proof of it or anything. It's very important. Okay, so in particular, you could think of a system where all of these states are embezzling. We saw that this is the case, and these are precisely the type 3-1 vectors. And in fact, if we have what's called an approximately finite dimensional ones, for example, in spin systems, relativistic QFT, actually the same holds for all mixed states. So in critical spin chains, in relativistic QFT, you get this embezzlement phenomenon in the strongest form you can imagine. So What does this tell us? Well, in a sense, it gives us an interpretation of the diverging vacuum entanglement in QFT if you remove the cutoff. There's also been a nice result by Stephen Summers and Reinhard Werner a long time ago, where they showed that you can maximally violate Bell inequalities in relativistic QFTs. And this provides a very nice way to do this. You just embezzle out a Bell state, and then you use a standard Bell test. OK. Now, there's also a problem. Okay, I should say this. Because here we assume that they can just apply arbitrary unitaries from these wedge algebras. This is not a very physically plausible thing to do. And there's a result or an argument by Sorkin that this is impossible. And it's unknown what are the true local operations that one could do in relativistic quantum theory, I would say. So this certainly suffers from this problem. It's an interesting open problem. OK, so what about this thing? Well, it turns out here you get type 2-1, here you get type 3-1. So this thing can embezzle if you have infinitely many copies, but this one cannot. So both have infinite one-shot entanglement, but only one can embezzle. OK, I would have to jump over the topological order, because I was reminded that I'm already over time. I want to say one thing about finite systems, though. So it turns out that if you say a spin system, and you know that in the thermodynamic limit your ground state is embezzling, like this, then it turns out that if you take a finite size version of the same system, you get an approximate form of embezzlement. And this is very hard to detect on the finite system itself. So this going to the thermodynamic limit, investigating the embezzling property, and then going back tells you something that it's hard to find otherwise. So this is very much like in phase transitions, which only become very clear in the thermodynamic limit. So in this case, you could say that these types are like an order parameter for what we call large-scale entanglement. And in maybe one small thing, also in QFT, if you fix a state and you fix an error, then Alice and Bob actually only have to act on a finite region. But these finite regions might be very large and might arbitrarily closely touch, of course, as you make the error smaller. OK, so the main takeaway here is that we have these algebraic properties of normal algebras, and they are one-to-one to entanglement properties that are otherwise difficult to find. So this is sort of the summary slide. And I want to mention one last thing. So these types of factors and Haag duality are properties that are preserved when you move finitely many degrees of freedom from one party to another. So they really don't depend on any finite modifications on your system, but only on what happens at infinity. So in this sense, they're really truly large-scale entanglement properties. And I think I will jump over the open problems because I'm already over time. So thank you for your attention. Here are some papers if you're interested in the details. Thank you.
Yeah, thanks. That was a very interesting talk. So does anybody have any questions? Yeah?
I found it very nice, the relationship between entanglement, pure states, and embezzlement, and the type of von Neumann algebras, right? But is there something similar to that would talk about entanglement for mixed states instead of only for pure states, and also like the distinction between the algebra types? Is there a classification, like a table, like the one that you showed for mixed states too?
So,
and a distinction?
Let me go here. This touches about this problem. So if you talk about mixed state bipartite entanglement, this is basically equivalent to talking about pure state multipartite entanglement via purification. And multipartite entanglement is notoriously difficult, as everybody knows. It turns out that you can construct abstractly systems where you have this multipartite embezzling property. So you have now 3 parties with the local actions, and they can embezzle any three-partite entangled state. It's an entirely open problem. So this is a constructive proof. We just write down a system that has this property. It's a super interesting open problem that is actually part of what I want to do in the next years, is to understand whether this phenomenon can actually appear in many body systems or maybe in quantum field theories even. Like you think of a one-dimensional, 1 plus 1 dimensional quantum field theory in a circle, and you take 3 intervals, then maybe that thing is already 3-partite embezzling. But this is much, much harder to classify, because now you talk about how these different factors relate to each other, these 3 ones, and you lose all the nice tools that are available. So currently we don't have such an understanding.
And what if A and B are don't share a boundary at all? What if they're separated? Would you expect something like this to hold there too?
Well, then, for example, in QFD, it doesn't hold because you have the split property, which forbids it. This is proven in this paper. So if you take Minkowski space, you take 3 causal diamonds, A, B, C, then you don't have this. But if maybe you have A, B, and then C takes the 2 outer ones, that could work.
But then you need to access the field in C as well to be able to.
Yeah. And then you have for the 3-dimensional thing, for the 3-partite thing, if you have a 3-partite embezzling state for pure states, you automatically have a bipartite mixed embezzling state for any of the 2 parties. I should have said that. This is proven. So you look, if you have a 3-partite embezzling state for pure states, then if you only look at 2 parties, they have a mixed state, and they can do bipartite embezzlement.
Sure, but in this case they share boundaries, so that's not surprising at all. But if A and B don't share a boundary, then I'd be surprised if you can embezzle between A and B.
Yeah, then you can't by the split, at least in QFT. Yeah.
All right, then let's thank the speaker once again, and the next speaker can start setting up.
How do I put this? Okay, like that.
Maybe you can change your screen settings to mirror. Or just pull the slide.
Maybe here. Here, yeah, okay. Yeah.
Very good. And the next speaker is Ruben Campos Delgado. He's a PhD student in our group, and he's going to tell you something about contextuality and relativistic quantum information.
Yeah.
The stage is yours.
Yeah, thank you, Martin, for inviting me today. Yes, so today I talk about basically about relativistic quantum mechanics. In particular, there is a notion in quantum mechanics called contextuality, which tells us that it's basically impossible to describe quantum mechanics using classical variables in a consistent way. Yeah, so they cannot be the prediction of quantum mechanics cannot be reproduced by classical variables, which are called hidden variables, unless the model that we use would be non-local and contextual, where contextual means something that I will describe later. But contextual means that you depend on how you measuring an observable A would depend on whether you measure another one at the same time. Yeah. So there are several notions of contextuality. One dates back to the 60s by Koch and Specker. There is a more general one, which is from 21 years ago, from 2005, which is from Speckens, which is the one that I will focus on today. So using this generalized framework, one can determine whether a model, by model we mean a set of preparations, set of measurements, is contextual or not. So the main question of this talk and of this paper of mine is to ask whether this notion, whether this generalized contextuality is an absolute concept, or if it depends on the reference frame. Yeah. Somehow no one ever, or at least when we talked about quantum information stuff, no one ever considered special relativity. But I decided to, when I was doing this research, I asked myself what happens if I switch to another reference frame. And so the answer is that yes. So the answer is that it depends on the reference frame, unless at least when you restrict yourself to spin degrees of freedom. So this means that if I am in my frame and if I measure a model to be contextual, it can happen that the other observer, which is moving with respect to me in another inertial frame, he can measure the same system to be the same model to be non-contextual. Yeah. This is true. This is always true, but only if we restrict to these spin degrees of freedom. So you can start with a state which has both spin and momentum. You trace out the momentum. You are left only with the spin degrees of freedom. Then you would see this effect coming up. But before we deal with the mathematics of all of that, I would like to describe this using an everyday example, which a friend of mine suggested me to be dancing. So you have here a random guy who is dancing. Now suppose that this person participates in a dance competition. Now we have two relevant frames. So the one of the dancer and the one of the judges who are judging the dancer. Yeah. So the dancer can say, oh, okay, I'm dancing very good, so I can describe the performance using his own hidden variables, right? So he can say, yeah, my performance was non-contextual because it is good, independent on which song I dance or independent on which partner I dance with. However, the judges, they have their own way to assign a score. Right? They say, okay, I see that guy is dancing good for this song, but dancing the other song he was worse, or he danced better with a girl, but she danced worse with another girl, and so on. So his performance will depend on the context. Yeah. Hence, the two descriptions are once in one frame non-contextual, and the other frame contextual. Right? So now replace the guy who is dancing with a quantum state, and then you have the result of this paper. Yeah, so first then I will describe briefly what contextuality is, then the Speckens formalism, then how do you describe qubits in special relativity, and at the end there is some implications to quantum information tasks. Yeah, so as I said before, non-contextual means that the measurement outcomes that you can have after you measure depends only on the Hermitian operator with this measurement, but not on which other Hermitian operators are measured simultaneously with it. We have a very, very famous result, which is the Cohen-Specker theorem of 1967. So this tells you that basically quantum mechanics is contextual in the sense that all these non-contextual hidden variable models, they are ruled out. So it's not possible to have them. So in quantum theory, you cannot consider measurements in quantum theory as revealing pre-existing values independent of the context. However, this traditional definition is it's an ancient definition coming from the 60s, so it's only specific to quantum mechanics. It applies only to hidden variable models, so there are some limitations. So that's why Speckens came up in 2005, so 21 years ago already. She proposed this new definition of what does it mean to be contextual or respectively non-contextual. So we have so you can think, okay, I have a physical theory with some primitive elements. Yeah, primitive elements are preparations, transformations, and measurements. And the goal of a theory is very simple. I just want to specify the probabilities for different outcomes that can result from a measurement, given some preparation procedure and maybe a transformation procedure. There is a notion of equivalence. One can define equivalence classes. So the two preparation procedures are equivalent if they give the same long-run statistics for every possible measurements. Two measurements are equivalent if they give the same statistics for every possible preparations. There are two types of features for an experimental procedure. A feature that is specified by specifying the equivalence class that the procedure falls in, or a feature where this is not possible. So the set of features of the second type form the so-called context of the experimental procedure. So in general, one can talk about an ontological model. So you can say, okay, there exists a physical system, and they have some attributes regardless of how I try to understand that. At any time, you can define an ontic state of the system, and if the ontic state is not completely specified after specifying the preparation, then you require additional variables, which are called hidden variables. Now, if you know that the system was prepared using preparation procedure P, you can model the system with a probability density mu. For every lambda, for every hidden variable, you can associate a probability density of obtaining the outcome K, given that the system was in the ontic state lambda. When if I have an ontological model where the representation of every experimental procedure depends only on the equivalence class and not on the context, then we say that the model is non-contextual. So mathematically, this means that these functions mu, they have to be independent of the context. So mu of P is equal to mu of E of P. So they depend only on the equivalence class. Same for this zeta. They depend only on the equivalence class of M. So when both equations are true, I call them either universally non-contextual or just for brevity non-contextual. So with this such a model where we have this mu, where we have this zeta function, you can define the probability P as a average summing over all mu, summing over psi averaged by mu. Yeah, so there will be the sum over the hidden variables. So in this case, an integral over lambda of mu of P of lambda times set of M of K of lambda. Yeah. So where mu, as I said, mu and zeta, they are independent of the context, depend only on the equivalence class. So this formula is true in general, but you can try to specify that for quantum mechanics itself, where, well, you know, in quantum mechanics, preparation equivalence classes are quantum states, so density operators. For measurements, you have either projective operator, but more in general, you can have POVMs. So a collection of positive definite operator with the normalization that they sum to 1. So with this, we have this definition of being spec-hence non-contextual for quantum mechanics. So it's very simple. So if this formula is true, if there exists some functions, some operator sigma lambda and g of lambda such that this formula holds for every state and for every measurements, then we say that the set of quantum states is spec-hence non-contextual. Yeah. So here one has to be careful about the wording, because when we say that a model is non-contextual, we in principle have to specify a set of states and a set of measurements. But we implicitly agree to consider all measurements. If we do this, then it's okay to define non-contextuality just in terms of states. Yeah. So I can just say, okay, this set of states is contextual or non-contextual. I can just forget about the measurements because I consider in all possible measurements. There is also necessary and sufficient condition about trying to check if the set is non-contextual or not. This was done by me and Martin in a previous paper. If the states are pure and they are linearly independent, then they are non-contextual, and vice versa. So it's an if and only if, but this works only if the states are pure. Yeah. Okay, and then with that, we can have a look at the relativistic qubits. So how do you perform a Lorentz transformation on a qubit? Well, one can show that these Lorentz boosts, they are implemented by a unitary operator U of lambda, where lambda is the Lorentz transformation in this way. So you sum over spins with some matrix in front. This D sigma prime sigma is a matrix, is a representation of the little group for spin S. So what one sees that at the end, spin and momentum become entangled after that I act on the unitary U. So consider these initial states, so psi1 to psi4. They both have spin and momentum, but suppose now you trace out the momentum. Then the states are the basic one, the 0, 0, the 1, 1, the plus, plus, the minus, minus. They are trivially pure and linearly dependent, hence, because of our theorem, they are contextual. But now you do the magic, you perform a Lorentz transformation, you go to the other frame, you trace out again the momentum, and you get the new reduced density matrices, where these I are just some integrals that I have defined. And now you can check that they are now linearly independent. You can check that it's possible to find a POVM such that this trace of the states with the POVM is delta J, which means that which means that now the definition is satisfied. So the left-hand side from this equation becomes trivially equal to the right-hand side, which means that now we are non-contextual. So the situation was the following. I have Alice on the one hand and Bob in the other hand. So Alice, she can perform some spin measurements on her states. She finds that the Speckens definition is not satisfied. So she says, okay, my model is contextual. Yeah. But then there is Bob. And Bob, we go to Bob. We are doing the Lorentz boost. Bob will observe the same states, but the states now appear different for him. Yeah. He now is able to find a pseudo PVMG of lambda such that the Speckens definition is satisfied. Yeah. As you can see, the definition here is trivially satisfied, because if I start with the left-hand side, then I recover trivially the right-hand side using that G of lambda equals to F of lambda. So the Bob's model, this means that the Bob's model is now non-contextual. Yeah. So there is a mismatch. Yeah. So Alice say, okay, I'm contextual. Bob says, I am non-contextual. Yeah. So this was an example where this happens. Yeah. There is an interest in applications, there is an interesting way to see what is happening for a certain class of quantum information tasks, which is the BB84 protocol. So Alice has some states. She sends the states out to Bob, and there is an eavesdropper. Eve knows that contextual can be mapped to non-contextual. So Eve wonders, what if I run so fast that the contextual states for me now become non-contextual? So Eve has the crazy idea of trying to break the protocol just by running very fast. So one can compute the probability of success for guessing the states which Alice emitted. But then what we find is that the probability of success actually decreases with the rapidity of the boost. So just by running, she does worse. So it's better for her not to run. It's better for her to stay at rest, because the probability of success is even lower than what it would have been if she was at rest. However, there is maybe a task where a moving observer can outperform one at rest, which is just by trying to distinguish in between two ensembles. In general, the probability for that is given by the Hellstrom formula. So this 1/2 plus 1 quota of the one norm of the operator. Now ρ1 is just defined, ρ1 tilde is just the sum of ρ1 plus ρ2 tilde is ρ3 plus ρ4. Now, since ρ1 tilde is equal to ρ2 tilde, then this is going to be 0, so the probability is 1/2. But for the transformed states, they are different, so then the probability will be 1/2 plus something, which means that the moving observer, the moving eavesdropper, has a slightly higher probability of guessing the state. I mean, this probability is a bit bigger, but not too much. As you can see, you go from 0.5 to 0.525. So it's a very tiny amount, but still it's still bigger than that. So yeah, so then we have seen that contextuality in general, when you think about contextuality, you have to remember that it is a frame-dependent concept. It's not an absolute concept. So when you say that something is contextual, you have first to say in which reference frame you are. So if you consider contextuality to be a fundamental concept, then you have to always talk about momentum and spin as inseparable. Yeah, if you want to insist for contextuality to be some fundamental thing. And then at the end, we saw that because of this way of how spin transforms, it is possible to have situations where a moving observer outperforms an observer at rest. An example was that of the task of the two-state discrimination. And yeah, so with this I conclude, and thank you very much.
Yeah, thanks. That was a very interesting talk. So, are there any questions? Yes. Wait for the microphone.
Thank you for the talk. That was very interesting. Question on the definition. Are you assuming that the eavesdropper is accelerating from rest by the rapidity of the boost, or that
no,
the eavesdropper...
I assume that the eavesdropper, he has already reached, so they are both inertial frames.
Okay, thank you.
He has already reached her speed, or yeah.
Okay, then if there's no more questions, let's thank the speaker again.
Yeah, thank you.
Let's set up the next talk. Very well, and the next talk and the last talk of this session is by Professor Michael Zopf, and this will not be a theoretical talk, but an experimental one about quantum networks, because there were several proposals about testing various relativistic concepts with quantum networks, and I'm very happy that we have here an experimentalist that's actually working on the networks themselves and will tell us what's the state of the art.
Yes, thank you very much for the kind introduction and also the invitation. Okay, yes, so what has been already said is that I will be giving an experimental talk. So it will change a little bit the style, basically. And since I thought, okay, you may not be aware too much about what we are doing, it's maybe good to give you an introduction and an overview about what we are doing. And also, kind of in the end, maybe make some little connection to possible questions that that could connect to your research, and I'm really interested if you have any good thoughts on that, on how that could connect. So yeah, my name is Michael, and I'm working here at the Institute of Solid-State Physics, basically just the floor below, and I will be talking about quantum photonic networks with semiconductor quantum dots. And in the beginning, I would like to acknowledge, first of all, my team members and also collaborators. So you see here also the team of Fei Ding, who is working here at the Institute, which I'm working closely together with, but also especially the collaborators at the University of Stuttgart, Peter Michler's team, and also Stefan Kück at the PTB in Braunschweig. Without those guys, the nice results that we had in the last years wouldn't have been possible. and of course also the funding agencies. Okay, let's start first of all with the question, what are semiconductor quantum light sources? What can they do? Why are they interesting? Now, I've seen from the first talks that you're interested in like this kind of infinite spaces and entanglement and so on. We are not that far yet experimentally, so we have some challenges to address. But semiconductor quantum light sources are really one of the best candidates for generating single photons and also entangled photon pairs, or also cluster states of photons. And why is that? So basically, you have three-dimensional confinement of charge carriers in a semiconductor matrix. And this three-dimensional confinement leads to discrete energy levels, a discrete density of states, similar to the case of natural atoms, actually. That's why semiconductor quantum dots are also often called artificial atoms. But there is a difference, of course. We are in a solid-state system, so there are differences to natural atoms. For example, we can tune their properties by designing our solid-state matrix. And also we have different types of noise that we have to address in these systems in our solid-state environment. Now, ideally, if you talk about a nice single photon source from a theoretical perspective, I believe you would want to have a perfectly efficient single photon source or entangled photon source, and also the different photons, they should be indistinguishable. And that is kind of experimentally really one of the challenges that the whole community is working on to achieve, and we as well. So for example, if you put a semiconductor quantum dot in a matrix, in a host matrix, usually their efficiency is just about 1%. So we basically excite a charge carrier with a laser here, we form an exciton, so an electron-hole pair, which then recombines and emits a single photon, and this photon is mostly reflected at the interface of our semiconductor because we have a high refractive index. And that means if we want to collect light from the top with a microscope objective, then only a few photons are coming out of that. And in order to address this, in the community, a lot of people thought about some nice photonic nano and microstructures to basically prepare and embed these quantum dots in, such as micropillar systems or micro lenses or circular crystal gratings, circular Bragg gratings, or also photonic crystal waveguides, open cavity systems. So there are lots of different approaches to this. And one approach that we used back in 2018 for entangled photons, for let's say extracting very efficiently entangled photons from semiconductor quantum dots, is to use a hemispherical lens that also has a high refractive index and then attach a quantum dot containing nanomembrane of semiconductor material at the bottom of that. And that was actually the first time where we could show that we have both a high entanglement fidelity and also a high pair extraction efficiency. So that is this data point here at the time that really goes beyond some state-of-the-art systems at the time, which are nonlinear optical materials with spontaneous parametric down conversion, which is basically the blue curve here. And basically the difference in the systems is you cannot pump them infinitely high, otherwise your entanglement fidelity would go down. So now, okay, we had a good entanglement fidelity and also an efficient source. And what you can then do is, for example, an entanglement swapping experiment. So we took two entangled photon pairs from this source, and then we performed a Bell state measurement on these red photons here. So basically a projection on an entangled state, and by that we then got an entangled state out of these two blue photons, and we could verify this experimentally, as you see in this two-photon density matrix that is basically the measured values, and this is the theoretical expectation, and with a fidelity of 81% we could measure basically a Bell state between these blue photons by doing so. So this is just to tell you semiconductor quantum dots can be used for generating photons or photonic states to test entanglement or to do quantum operations on. Now the thing is, semiconductor quantum dots have, I believe, really a strong potential for the future. And one of the reasons is, so if you look at this picture, this is a wide field photoluminescence image. So we just hit our samples with laser light over a large area and excite a lot of quantum dots on our wafer. And these quantum dots emitting, you basically see every one of these white spots is a quantum dot. And we also fabricated some gold markers on this sample. So here you see that basically there are really a lot of quantum dots. So this is 10 micrometer. There are really a lot of quantum dots on a single wafer. And they have a strong potential as single and entangled photon sources, this I already mentioned, but also they're very fast, especially in comparison to natural atoms. So they can operate at gigahertz speeds. And also, they can be used as a spin qubit. So for example, you can trap a charge in these quantum dots and then use the spin, manipulate and read out the spin to investigate some physics and also noise in these systems. You can use semiconductor technology for scaling these system up, and also they can operate at telecom wavelengths, which, as I will show later on, is important for fiber networks or for sending these photons on fiber networks. Okay, so until today, most of the time, basically in our community, we do lots of fancy fabrication techniques until we have one device that kind of contains only one quantum dot. And there are relatively few examples in the literature where people really try to investigate more than one quantum dot and try to somehow see how they can interact and study some cooperative effects. But if you look at this image here, you see there are actually so many quantum dots and all of this on a chip. So there is a lot of potential to go or to study their interaction. And when I talk about photonic quantum networks, I understand this in kind of both ways. And this is also how my talk is now structured in two parts, starting from integrated quantum networks. So just the thought of how can we in the future get to a place where we have a lot of quantum dots interacting on chip, or let's say the photons from these quantum dots or the spins in these quantum dots, and then towards using quantum dots in distributed network settings. So let's say existing fiber networks that are powering classical communication today. So when you write a message on WhatsApp or so today to your friends somewhere on another continent, that basically goes over the intercontinental fiber networks, for example. Let's start with integrated quantum networks. And for that, I would like to introduce to you a bit more which material system we are working on. So we are mostly focusing on gallium arsenide quantum dots embedded in aluminum gallium arsenide, which is a very beautiful material system because gallium arsenide and aluminum arsenide, they have very similar lattice constants. So when we bring them on top of each other, there's low strain basically and low additional noise that we introduce. And that gives us a high level of control. And we do this with a molecular beam epitaxy machine that is sitting in a building next to here. And if you then deposit aluminum on an aluminum gallium arsenide surface, it forms small droplets. And under the right conditions, you can form little nanoholes on the surface. And these nanoholes can then be filled with gallium arsenide, which has a lower band gap than aluminum gallium arsenide. And then we can cap this with aluminum gallium arsenide again. And like this, we get three-dimensional confinement of charge carriers in such a systems on very small scale. Now, as I mentioned, we have a good level of control because now we can just use the amount of filling material to tune the confinement in these systems. This is what you can see here. So for example, you can use less material or more material and then tune the emission wavelength. So this is a photoluminescence spectrum here. You can tune this from, let's say, 737 nanometers to around 790 nanometers, which is also very interesting, especially if you want to consider connecting to other quantum systems which maybe live at this wavelength range. Okay, but how do we now get to many or interaction of several dots? And we can get to that, or we usually want to study this, or what we experimentally do in our community is typically study homomundal interference between photons emitted from different quantum dots. So in this case, we first need to go to 2 before we think about going to many. And what that means is that if we send photons into a 50-50 beam splitter, and if those are indistinguishable, then what we can eventually detect is only the photons that are coming out together at the beam splitter output. So only those 2 cases survive. And we've also verified this. So we basically built 2 separate devices. We put them in 2 cryostats. So I need to say we need to cool this down to 4 Kelvin for this to work nicely, because the solid state environment otherwise makes lots of noise. And eventually what we did here is we had 2 samples, 2 quantum dots emitting single photons, and we locked the emission to a rubidium-based Faraday filter so that they would be exactly at the same emission frequency. And then we performed Hongo-Mandel interference experiments, so the beam splitter and 2 single photon detectors. And if you then look at the coincidence histogram, so basically when there is a coincidence, or you measure the time difference between the 2 detectors over the time delay, and then you can see that in the case that you have 2 parallel, both photons are parallel polarized, that the coincidences at this center peak are suppressed, which basically means exactly what I've mentioned before, that mostly the 2 photons are detected that are leaving together at the output of the beam splitter. If we now deliberately make them distinguishable, that is the black case with orthogonal polarizations, then this is basically leading to larger coincidences. So also the cases where you detect photons at both detectors at the output at the same time. And we measured the visibility, which is basically corresponding to the indistinguishability of the photons, of 41% in this case, which was fundamentally limited by a cascade process internally. And by now in the community, it's actually possible. There has been some beautiful work that show that we can go above 90% of indistinguishability from different quantum dots. So this is kind of an experimental challenge already, as you see, to get to these indistinguishabilities, because every quantum dot is kind of different. It's not like, an atom is kind of an atom. Of course, if it's in an external field and so on, you need to take care a bit, but a quantum dot, it can have some atoms more, some atoms less. The strain fields or other fields, they can be different from dot to dot. So every quantum dot is a little bit different. So we need some kind of tuning. And that's why we are investigating local tuning techniques, so that on the chip, basically, we can tune different quantum dots in resonance with each other, so that we can, in the future, study their interaction. And one example of this is using strain. So we use piezoelectric actuators, so basically stretch and compress the quantum dot nanomembranes. And if you then look at 2 different spots of this nanomembrane on the same chip, we apply an electric field to the actuator and then look at the photon energy. You see that we can tune these 2 quantum dots that are sitting on the same chip into resonance with each other. Since we are in a semiconductor system, we can also use diode structures and vertical electric field. That's what you see here. So here you see the wavelength, and here the bias voltage that is applied to one of these devices. And you see that also here we can spectrally tune. One more advantage of this system is that we can reduce noise in the quantum dots, because it's not only about tuning these into resonance with each other, it's also about reducing their line width to their fundamental limit. And basically these structures help to do that. And also we are working on lateral fields, so basically electrodes that tune the electric field laterally with one quantum dot that sits here in the center, where you can also see that basically we can tune actually not only the wavelength, but also a lot of other interesting things. Okay, so when you kind of have dealt with the local tuning, then you still need somehow to find a way to deterministically integrate those things into photonic structures. That's kind of the next step. And there comes the next experimental challenge, because if you look at this picture again, you see basically the quantum dots, they are just all randomly distributed over the sample. And that means we need to figure out first where are these quantum dots exactly, and then fabricate photonic structures exactly around these quantum dots. And we need these photonic structures because we want to have a common photonic mode so that the quantum dots can eventually talk to each other. And the accuracy we need is around 25 nanometer. Now, there has been an approach since several years already in the community to do optical positioning. So basically our fabrication devices, they can detect these gold markers. And then if you know from such an image where a quantum dot is exactly, you can fabricate a quantum dot around that. One of the problems we faced is that you need basically imaging systems in your cryostat. And these are typically not as well designed as the commercial imaging systems at room temperature that you find these days. And sometimes also they change from measurement to measurement. So we actually developed a calibration routine for this, which works like this. So we deterministically fabricated first some very small gold structures that kind of look like quantum dot in an image like that. But the difference is we know exactly where they are. And if we know exactly where they are and we put them in a cryogenic imaging system, then we can basically correct the optical aberrations and then write photonic structures around that, such as, for example, some nanodisk structures like this. And this is just to show you that basically now we have the possibility to integrate a lot of these quantum dots on the chip on deterministic positions. And then eventually what you want to do is you still want to integrate that in, for example, waveguide systems. Now I will not show you all the details here because we are really not yet there that we can couple a lot of quantum dots to each other, but I think we are on a good track. So this is a photonic waveguide. So basically the light travels inside this waveguide. And if you put two quantum dots in here, they can be in a shared photonic mode. And then you have a grating coupler that is used for in and out coupling in and out of the chip, like light in and out coupling, for example, for laser light, but also the quantum dot emission. And if you look at this wide field photoluminescence image again, you see that we found a structure where two quantum dots are in the same waveguide and they also emit then through the grating coupler of chip. And then, for example, you see these photoluminescence spectra collected from here of these different quantum dots. Now, they are not one of the most beautiful ones yet, so we still need to deal with some noise and other things, but you basically already see that you can integrate several dots in these systems using these techniques. Okay, so this was kind of the first part to show you what can be done in the future with quantum dots and integration. Now, of course, we are not the only ones working on this. The whole community is trying to make advances here, and there are a lot of beautiful advances in this direction. And from here, the next question is, how can quantum dots be used in distributed quantum networks? So now we are not thinking anymore about how they can talk to each other on a single chip, but maybe how they can talk to each other on a fiber network in the future between different cities. Or also just in general the question, how can the light states, the non-classical light states that quantum dots emit, can be used in a distributed network setting. And just to make a transition from what we have just talked about, I have let you know before that quantum dots have this advantage that we can tailor their properties. Yeah? We have a solid state matrix. And we have, for example, worked on, and other colleagues in the field have worked on similar systems too. We've worked on a quantum dot system with a different material, basically indium arsenide and indium phosphide system, and also designed its properties in a way that when you look at the photoluminescence spectra, you have now different wavelengths. So these wavelengths are in the telecom O band, for example, at 1330 nanometers, or in the telecom C band. And why is this so important? It's just that in fibers, the transmission losses are the lowest for these telecom bands, especially here for the C band. If you want to do really intercity quantum communication or something like that, you want to have low transmission losses if you want to deal with single photons that you transmit over fiber. And then we use some photonic structures to enhance their brightness. And here, this is a measurement of the second order autocorrelation, just to prove that we really have a nice single photon source. So this is just to tell you, okay, with quantum dots, we have one decisive advantage. We can tailor their properties so that we have a good single photon emission, or also entangled photon emission, at telecom wavelengths. Now, in the last decades and years, there has been a lot happening in quantum communication since the first experimental demonstrations of quantum key distribution experiments that have been basically proposed in 1984 already. And you see that in North America, Asia, and Europe, over the years now, there are a lot of quantum networking testbeds popping up. So this is really a growing area of research and technology. And there are a lot of interesting questions that you can work at on such quantum networks. And now I need to see how much time I have. Okay. So let's just now think about one particular application for quantum networks. And this is quantum communication. And I just want to motivate why quantum communication is important. Give you one example that one of our students, Joscha, has found. I think it was Joscha. So basically, Operation Rubicon. I don't know if you've heard of it in the past, but basically these are some devices used for encrypting and decrypting messages. And in 1970, basically the company Crypto AG, which fabricates these things, was bought in secret by the US and West German foreign intelligence agencies. And what happened is they took secretly control of this company and they modified the encryption techniques so that they could basically read the messages that diplomats around the world, so you see all the red affected countries here, use for encrypting their messages. And of course, that's something as a country that you don't want to happen. You need this security. And I think now in the times of artificial intelligence and so on, I don't need to tell you how important it is to have this kind of security in that your data is safe and that you can transmit messages in a secure way. Now, what is the difference now to quantum communication or the quantum key distribution? It's nice that the BB84 protocol was mentioned before already. So basically here we rely purely on mathematical methods for encryption, are more vulnerable to backdoors, and we don't really detect eavesdropping as proven by history in that sense. And on the other hand, by quantum key distribution, we rely on quantum physics as the fundamental principle, especially the no cloning theorem, which basically, or where the key point is that eavesdropping will be detected. So we want to generate a key that we can use to encrypt securely our messages. And when somebody intercepts this key, then we would detect that and we basically know that the key is not safe. And since I'm not sure if everybody knows how quantum key distribution works, I would just like to give a brief introduction to what we do also experimentally using the BB84 protocol. Basically, we have a light source, in our case a single photon source based on a single quantum dot. And this light source sends out single photons, and now we encode information using the polarization state of light. And we can use two different basis sets, the rectilinear basis, so horizontal or vertical, or the diagonal basis to encode this. And Alice now chooses in which basis to encode and also chooses which state to send. And basically in this basis, horizontal would be 0, vertical would be 1. In the diagonal basis, these two states will then also correspond to a 0 and the one that Alice is sending. And then it's sending all this information, the quantum signals, over a channel to Bob. And Bob now chooses randomly the basis that he's measuring in. So basically the rectilinear basis or the diagonal basis. And then he measures an outcome, measures basically a 1 or a 0. In this case, he measures 1. And here you see the basis of send bit was in the rectilinear basis, and here in the diagonal basis it was measured. So it's basically useless eventually, this bit. It's not really compatible. But the next time it was sent here in the same basis and also measured in the same basis. So here that's basically now a value that we could take for the key. And now this continues. Here it's different again, so it's not compatible. And it goes on and on and on. And then eventually you can get to shared key bits. Now, of course, there are some additional tricks to play here, but you eventually get to shared key bits where these bases are the same. And what happens is that the basis choice is revealed over a classical authenticated channel to, like, from Alice to Bob. And like this, they can basically then exchange their key. But basically, the basis choice can be seen by an eavesdropper, so that's not a problem, but it needs to be an authenticated classical channel. And then what you can do is you have, for example, an original message, such as the smiley. It's basically a pixel image where this is 0 and black would be 1. So this would be the message. And then you can do, you have a key that you obtain from quantum key distribution. And then if you add this key to your message, basically have a simple form of a one-time pad encryption. And that gives you something that is not recognizable anymore, so the encrypted message. And then Bob can decrypt this again, because basically he has retrieved the same key, or Alice and Bob, they have secretly shared a key with each other via quantum key distribution. And then you have a message encryption again. You have the message decryption so that you get the original message back. Okay, so what did we do now experimentally? So experimentally, we have a quantum dot device from our colleagues at the University of Stuttgart that they fabricated that emits in the telecom wavelength range. So here you see the photoluminescence spectrum. So it's nicely emitting in the telecom C-band, and it's also very bright. You see the photon count rate at the detectors over time is around 3.6 million counts per second. And basically for every excitation to the quantum dot that we make, we get around 14% chance to get a single photon out. So this quantum dot sits now here in Hanover. And yeah, this nice animation is basically trying to show what's going on. So the quantum dot is embedded in such microresonator structure to make the emission more efficient. And then we modulate the polarization state of the light, of the single photon that is emitted. And then basically the single photons, they are coupled in a single mode fiber. And the single mode fiber then travels here through the city of Hanover to the city of Braunschweig, without any repeater stations, so it's just a dark fiber that we use here of around close to 80 kilometers. And then at the PTB in Braunschweig, the polarization is decoded again, and then the measurement of the single photon takes place. So that's exactly what you would do for the BB84 protocol. And what we, let's see, okay, anyway. So what we basically then looked at is the secret key bits per pulse, so per excitation pulse, that we can share over a certain distance that corresponds to a transmission loss. And we had a transmission loss of around 25, 26 dB. And this star here is the data point over the dark fiber, basically. And these blue and orange curves, they are measurements in the lab. And we were here really the first to demonstrate such an intercity quantum key distribution experiment with deterministic sources of single photons in the telecom regime. And that was also giving us really a very high secret key bits per pulse. And we also saw that we are kind of getting close to some other state-of-the-art implementation of quantum key distribution protocols like decoy state protocol, for example. Now, okay, what we did here was, to be honest, not yet really a full implementation of QKD, because you need a lot of things to really make sure that QKD is secure. And what we did here is we basically manually rotated wave plates in order to encode polarization states, and then using passive decoding at Bob's side. But what we need is actually an ultra-fast modulation. So I told you these quantum dots, they can operate at a gigahertz rate or close to gigahertz rate. And we have here a fluorescence lifetime measurement that tells you, okay, we have a lifetime of around 1 nanosecond. So we can operate this close to gigahertz, and a single photon purity of 0.55%. So that's also very good, the G2 value. And now what we did is we built an ultra-fast polarization encoder in order to encode polarizations in a faster way. And we did that using a Sagnac loop interferometer, which basically helps to make this encoding more stable. And what we have basically then is a phase modulator to which we apply a voltage at a given time, which modulates the phase. And then we can, after this setup, have photons that are anti-diagonal or left-hand circular or diagonal or right-hand circular polarized. So we use the different polarization bases here. And then you can see, so this is basically the voltage over time. So this is time in nanosecond. And the different voltage then corresponds to a different phase and hence to a different polarization state. And you see that we could modulate this with 152 megahertz. So that's kind of what we need. That's very fast. And also have a reasonable loss that can be also further improved with more optimization. And we got a mean quantum bit error ratio, which is kind of the property you want to look at after adding more elements and adding more modulation, of 0.7%, which is extremely low for such kind of active modulation systems. And this is something we're very happy about. Now, a similar setup was also used to realize time-bend QKD using quantum dots over a fiber. This was now a fiber spool experiment of 120 kilometers. So why are we also interested in time-bend and not only in polarization? We are interested in time-bend because polarization basically suffers from birefringence in the fiber. I mean, the environment changes, the temperature and everything, or maybe mechanical vibrations, and that changes polarization states. So if you have a time-bend state that is just more robust against these kind of things, and we used now an interferometric setup, again a Sagnac loop, in order to create these time-bend states in a stable way. And without going into too much detail, we basically have an encoder, the optical channel, and then basically, depending on if your state or if your photon is sent in the early or late time bin or superposition, you can then use this as your quantum state and decode this again. And then we basically can also plot again the secret key bits per pulse. This is here the blue curve. And we see that we have a maximum distance of around 120 kilometers we can achieve like this. And also the quantum bit error ratio, if you plot this over time, you see that this is just a very stable system. Yeah? Okay, so now I've shown you what our, like what we are doing in terms of QKD. But if we want to go beyond QKD and actually think about quantum networks that maybe where you have local nodes of different quantum dots that want to talk to each other, or you want to perform Hongo-Mandel interference over a larger network, you need synchronization. So you need basically in Hanover and Braunschweig to have the same timing and the same frequencies of your systems and to synchronize them in order for the two photons that are emitted to really hit the beam splitter exactly at the same time and to measure Hongo-Mandel interference. And what we are doing is we want to kind of get rid of more complicated time and frequency synchronization systems and use the quantum signal itself as a resource for synchronization and for retrieving time and frequency information. Because when you measure basically on a single photon detector, like in Braunschweig, for example, yeah, or the second single photon detector you have this kind of binary this kind of binary function here, where the 1 basically tells you, okay, I've detected a photon, and 0 is I have not detected a photon. And if you then do a Fourier transform, you basically find the frequency at which your quantum dot is excited at. And this frequency you can then use, and after some fine-tuning, basically to recover the time and frequency of the signal. And that's basically what you see here. So the drifts of the rate and the time, which you can really keep stable over time by just looking at the quantum signal, and by hopefully allowing us in the future to reduce the amount of resources we need to run quantum networks. Okay, now in the end, I want to give you a summary and an outlook. So first, I hope that you're convinced together with me that semiconductor quantum dots have significant potential both for integrated quantum networks and also distributed quantum networks. And on the last slide, I want to just give you a bit of outlook for applications of distributed quantum networks, also those that go beyond quantum communication and that we are in principle also interested in. So quantum communication, I've talked to you about quantum key distribution in particular, but you can also do distributed quantum computing. So if you have quantum computers sitting at different sites, you basically can use algorithms that work on different quantum computers that are distributed, and that has also interesting implications for security of these computations. You can do distributed quantum sensing. So for example here, 2 entangled quantum memories that are spaced apart, they can be used for increasing sensitivity of interferometry. You can look into quantum clock synchronization, so how quantum signals can be used to maybe synchronize clocks in a more accurate way than by classical signals. Or also you can use it to think about or kind of closing loopholes in Bell inequality violation, which is also a very interesting topic. I remember a talk by Brassard, who was one of the inventors of the BB84 protocols, who is kind of not very convinced that local hidden variables should be the only way of connecting to local realism, and that there can be thought experiments that basically violate Bell's inequality, but are also locally realistic. So I think it's very interesting, but maybe you know more about that than I do, so I've just heard a talk about him. So yeah, this slide is basically there to invite you also to have maybe some questions or discussions later on. So in case you have any interesting ideas on what could be done on such a test bed, we are always open for some discussions and collaborations. And with this, I would like to thank you for your attention.
Thank you for the very interesting talk. Are there any questions from the audience? Yes.
Hi, just a small question. Did you get a chance to read a very recent paper that came into spotlight about authors? They found a way to bypass the no cloning theorem. Then that would affect the whole QKD setup, right?
I'm sorry, what were they able to bypass?
I think in the paper, I just read the abstract where they found a way to bypass the no cloning theorem, that they somehow proved it to be false.
Okay, no, I didn't see that yet. Maybe we could talk afterwards. Then. Yeah, thank you.
Maybe one question for the fundamentals. I'm interested because I work in Paderborn with parametric down conversion. Do you have any limits on the gain of your when you pump your quantum dots? Because typically when we want to produce single photons or single photon pairs, let's say, we typically work in the low gain regime, because when you go to higher gain, then you produce squeezing and the time ordering typically kills you. I suppose you have some problems then with the cooling, but other than, do you have other effects that you have to account for?
Yeah, thank you. Yes, so I would say I think the best experimental demonstrations at the moment for efficiency of single photon sources with quantum dots. They're about 70% around. And yes, there are some limitations that go beyond that. I think they can be addressed with enough engineering of these systems. Like maybe we don't get perfectly to 100%, let's say. I think there are lots of challenges both in the integration, like kind of which cavity system you're integrating in, but also sometimes you can have coupling to phonons or other effects that can reduce this efficiency. But I would say there's not, let's say, a fundamental limit of the gain similar to nonlinear sources. But on the other hand, we have also some more experimental engineering challenges in these systems, I would say, compared to nonlinear sources, especially in terms of indistinguishability and tunability and so on. Yeah.
I'll maybe have a last question, because you were talking about timing in the networks. Have you had to deal there with any relativistic effects?
So far, I think so far not yet. I mean, we are, well, okay. I mean, we are dealing with photons. Yeah, so I cannot recall that we directly have to account for relativistic effects, but I know I've read some papers that are taking these things into account as well. But so far we didn't measure anything that would kind of go in this direction. Yeah. But,
okay.
But you could kind of, yeah, I remember some papers that are investigating this. I mean, maybe if you have some interesting idea or so, we could discuss that. Yeah.
Okay, then let's thank the speaker again. And this concludes this session. We'll now go for lunch. If you're not from Hanover, just follow somebody that's from Hanover, and we will meet all here at 1 o'clock for the next session.
Hi, welcome back to the RQI circuit. So it's a pleasure to now introduce Alexander Stottmeister as an online speaker. He's a postdoc in Hanover here, and he will talk about real-time lattice approximations of quantum fields. So please go ahead.
Yeah, well, thanks to the organizers for, on the one hand, inviting me, and on the other hand, making this short notice switch to online talk possible. So as Henrik already said, I want to talk about real-time lattice approximations of quantum fields and potential applications to quantum simulation, quantum computation. So this is a kind of ongoing project I have for a long time with various authors. A few of them are named here. Or people in Hanover, in Rome, and elsewhere. And okay, so we start with the first slide. So of course, you could first ask the question, okay, why should I actually care about quantum field theory at all? And then, I mean, one of the maybe more convincing answers is that it describes quantum systems with infinitely many or unbounded many degrees of freedom. And well, it has been used to capture some of the most complex phenomena in physics. So on one hand, in high energy physics, you have the predictions for the hadronic mass spectrum and of course the standard model, as we all know. And then in condensed matter physics, it has also been used, for example, for explanations of the fractional quantum Hall effect and the theory of phase transition. Plays an important role. If you, for example, want to expect critical exponents close to phase transitions, then formal field techniques are relevant there. But now, why should this matter to, let's say, quantum computation or simulation? Well, this does, I think, in the sense that quantum simulation algorithms or in general quantum computers promise that we can get like new non-perturbative insights into quantum field theory, because most of what we know so far about quantum field theory or say physical phenomena that are described by those are based on a lot of perturbative calculations or on like very high effort, high performance computations that can extract certain data where let's say Euclidean statistical mechanics approaches. But yeah, quantum computers offer like the prospect of directly simulating the dynamics of quantum field theories, or in general quantum systems, and then maybe also quantum field theory. Okay, so and just to give you also an impression of what one is up against, so this is like a picture I took from the science paper or graphics where they did an like ab initio computation of the hadronic mass spectrum. So you see that they use some of the light hadron masses as input parameters, and then they do via lattice QCD calculations. They calculate all the other masses from it. And of course, that's something where probably quantum computers can for some time not compete with, but that's a challenge for the future, I would say. And okay, so we go on. So in the beginning, where I posed the question, why quantum field theory? But of course, you should also ask, what is quantum field theory in a sense? So, and the first disclaimer would be, well, this is not a really fully settled question, depending on your mathematical taste for rigor, I would say. Because we understand quantum field theory pretty well from a perturbative point of view and in low dimensions, but in like a non-perturbative sense, in like the natural space-time dimension 3+1 or 4, we do not really have a good mathematical theory of quantum field theories. But for this talk, I will basically follow Wilson's approach, and we will think of quantum field theories as a kind of consistent sequence of scale-dependent effective field theories. And the actual quantum field theory should be the would-be consistent object that is behind the scale-dependent sequence, which is to be constructed. And these effective models, they are linked by the so-called renormalization group, and that describes how we transition between the different scales in a certain sense. And one important assumption that one should be aware of in this framework is that underlying this renormalization group idea is always the idea that successive scales are only weakly coupled. So there's not much interaction between like well-separated scales. And in this whole viewpoint on quantum field theory, conformal field theories are kind of singled out as fixed points of the renormalization group. And that's why they are important to phase transitions and lead to this idea of universality in physics. Because basically you have these fixed points, and everything that is around these fixed points is either kind of repelled or attracted to these fixed points. So it's kind of governed, the overall large scale structure is governed by these fixed points. Okay, and well, I've made a little sketch here of how you could think about that. So you can think about this effective field theory picture by, let's say, these planes, which indicate different scales of your physical system. So let's say physical resolutions of your measuring devices that you can probe the physical system with. And then each point in such a plane would correspond to a specific description via, let's say, a Hamiltonian of your physical system with some input parameters. And the RG flow then is essentially a map that tells you how to move from one of these planes to the others, and it connects like these various Hamiltonians to one another by acting essentially on the space of coupling you have. Of course, that's a kind of very formal picture. To make that rigorous is really difficult. And the idea is then that a quantum field theories or a continuum model is actually something where you follow these flow lines, and then you try to get like to this bottom where at the fixed points are the CFTs, and slightly away from that. So you have the field theories, which are then governed in a sense by a consistent sequence of coupling constants that remain finite at this bottom level. Okay, much for that. So now, how does this help with understanding how to simulate quantum field theories? Well, I think it was already kind of hinted at in the talk by Pascal at his lattice 2018 conference, that a good idea would be to exploit the renormalization group paradigm to actually get a handle on simulation. And the idea is that, in a sense, the quantum simulation of an effective field theory is, of course, only relevant to a given energy scale. So, and in a sense, if you now want to simulate the actual quantum field theory, you need to understand also the linkage between the two. And here I want to even be more concrete in the sense that the energy scale is fixed in the sense that we are looking at lattice field theories. So in a sense, the minimal length sets in these models sets something like the energy scale at which we are probing the system. And but there's been a lot of previous work on this stuff where people looked at lattice gauge theories, but at specific scales, bosonic and fermionic theories. But and all this works relatively well. Let's say, for example, if you look at the massive bosonic field theory, because then the natural mass scale or the energy scale of the system is kind of set by the mass of the field. So you could argue that if you get to a lattice resolution where you are sensitive to this natural energy scale of the system, then you do not really need to go any further. The lattice refinement, or maybe only slightly beyond it, until to capture all the relevant phenomena. And but so this only works if you have something like this natural regulator built in. So from this point of view, conformal field theories are especially challenging because you don't have conformal field theories are especially theories that are scale invariant. So you cannot have like a built-in intrinsic mass scale, or energy scale. So if we kind of want to understand conceptually how to simulate quantum field theories, I think it would be a good idea to also address this issue. And then maybe we can get even better insights into the simulations of field theories where we are looking at models that have an intrinsic energy scale. And okay, so the main upshot of the talk then would be that, okay, get a handle on quantum field theories without using these intrinsic cutoffs, well, that can be done by using this renormalization group idea, in the sense that we use the renormalization group flow to control the approximation errors that we are making when we are putting a model on a specific lattice. And the idea would be, so I sketched this here like as a representation of what we want to get at. So what we are interested in are dynamical correlation functions typically. So we have like a given lattice model at a scale n, so that would be this index n here. And then we can look at observables at this lattice scale. We have some dynamics on this lattice scale by discretizing the model in an appropriate way. And we can compute the dynamical correlation functions at this scale. So that's what people typically do. Now we basically want to understand, okay, how far is this away from the potential continuum limit? So, and this would be this other quantity here. What we want to estimate, or what we want to get a handle on, is like the difference of these two quantities. Ideally, in terms of a bound on how, so this t would be the time scale at which we are having a controlled error. And then we have the scale of the lattice n. And then now the kind of maybe natural idea is that instead of using a inbuilt length scale for the quantum field theory, you're just associating the length scale with the observables you're actually looking at. So you're now distinguishing the simulation scale, let's say, that's the finest resolution you can achieve on the lattice from the actual resolution you want for the observables that you're looking at this lattice. And that's these are basically the quantities that should control this error. And yeah, and to make this mathematically more precise, it makes sense to take some intuition from like the conceptual analysis of quantum field theory. And in particular, in this case, what we did is like we try to take inspiration from constructive approaches in quantum field theory, so how to construct them mathematically rigorously, and from algebraic quantum field theory. Okay, and the idea is now to praise basically this renormalization group approach in an operator algebraic language, so that we can make precise statements, about objects like this, about these difference estimators. Okay. And so what we need for this is essentially a couple of input data, and then we need our sequence of effective quantum systems. So where you could think of having an algebra of observables or fields, that is A n here for every scale n. And let's say n is some logarithmic scale parameter in the sense that, let's say we have a lattice with a certain number of sides, and for every n we double the number of sides. Or depending on the dimension, we take 2d times the number of sides. So basically we're halving every side once we increase the scale. Then we have some Hilbert space for the specific situation, which we associate with that lattice, and some effective Hamiltonian that's like our favorite discretization of the model at that scale. And then what we also need is like a sequence of initial states. So which, for example, I mean, natural choice, since we are looking for quantum field theories close to conformal field theories in the continuum, we basically need initial states of our Hamiltonian system that are critical, in the sense that we think of our Hamiltonians as depending on some coupling constants, and we take the ground states close to the critical points of the system. Otherwise, there's no chance of extracting a sensible continuum theory, because if your model is not critical, I mean, what does criticality exactly mean? It means that your correlation length diverges in terms of the lattice spacing. But since the lattice spacing is not physical, so this you want to take to 0 in the end. So to get a finite correlation length, in the end, you need a quantity, you need to have it divergent if you measure it in terms of the lattice spacing. So that's why you need to be close to criticality to get something that has non-trivial correlations in the continuum. Now the third input would be some RG channels that describe how we move between the different scales. And here we basically take a kind of Heisenberg picture version of the usual RG idea. And so instead of, let's say, coarse graining our states, which would be these E maps, we like take the conjugate or the dual of these maps, and we think about fine graining observables. So the idea would be that you have an observable at a given scale n, and you need to understand to move to the next scale how this decomposes into observables once you move to a finer scale. And of course, there's some arbitrariness in how you should do that, and that's basically some model-dependent input, if you want. Okay, then let me make it a bit more precise how we now extract the continuum limit or how this should work. So this is like basically an analogy of a figure that Wilson already used in a Hamiltonian setting. So the idea is that you form this kind of triangle. So at every horizontal line, you have you have a fixed scale at which you are considering your system, and then you take your initial sequence of states, which is here on this diagonal, and now you produce this horizontal sequence of states for a fixed scale by basically pulling down the critical states or the close to critical states from the scales above. And this defines a sequence of states for a given scale, and you can ask whether this has a limit. And basically, if it has a limit, then that thing is something that behaves naturally under these pullbacks. So it has this property that automatically defines something or some state on a system that is formed out of all the possible observations you can do over all scales. So this is how you could think of this A infinity object here. So this is like telling you that if you take any, let's say, basic observable or field object in this A infinity thing, then that's something at a fixed scale, but the selection of the scale is arbitrary. And the statement that if you have these horizontal sequences converging means that you get a consistent collection of density matrices, let's say, or states on these observables that in this sense you define a quantum field theory or a continuous model. And I indicated some references where we have made this precise for specific simple models. For example, if you take a lattice fermion model or something like the transverse field Ising chain, which has a nice critical point with some non-trivial behavior, then you can carry out this procedure explicitly and get the expected continuum field theory out of that, which is in that case an algebra of observables that describes the continuum system and the state on that, which is kind of the vacuum state of the quantum field theory in that case. And you reproduce like a usual Hilbert space formulation by doing something like that's called the GNS construction, which basically means you construct the Hilbert space by from all the inner products you can generate from observables and the state, or basically all the correlation functions you can get in this one. Okay, and now let me illustrate this a bit in more detail how to do that for, say, bosonic and fermionic field theories. So in that case, essentially, say, free field theories. So in that case, your effective models, you can think of just as second quantized field theories on a given finite lattice. So let's for simplicity stick to 1D for the picture. So and we construct it in finite volume, so that we are basically working on a one-dimensional circle where the fields live, and we want to construct a quantum field theory for that. So how you do that is basically you partition your circle into like a given number of sites or intervals, and then you look at like the fermion or boson algebras over this lattice, which basically means that you do a second quantization of the one particle space, which is just all the functions on this discretized version of the circle. And one instance would, for example, be the transverse field Ising chain if you go to its Majorana representation. So you do the Jordan-Wigner transformation from spins to fermionic operators. And if you do that on a finite interval with periodic boundary conditions, you would be in this setting. And the initial states you can take then are the ground states, as I said, of your Hamiltonian, depending on some coupling. And let's say to be explicit, in the transverse field Ising chain, you have the two couplings. One is the transverse field, so transverse magnetic field, and the other one is the spin-spin coupling. And if they are of equal size in a sense or strength, then you're at the critical point where fluctuations are like all over the system. And now you try to take this limit in the sense I was talking about before, and you do this by constructing certain RG channels. And these RG channels are now, that's your design task, how to choose them. But here we can basically exploit like this quasi-local structure of the CCR and CAR algebra over a finite Hilbert space. And the idea then is, okay, since these algebras are formed from annihilation creation operators for the bosons or fermions, what you do is you say, okay, if I have one of these operators at a coarse lattice, then okay, how should this decompose at the next scale, where it should be kind of linear combination, because we have the linear field theory of operators that are close to the original lattice size. If you think about it geometrically, and well, then this basically means that you say, okay, you map this one operator at a point to a linear combination with some weights. And if you think a bit about what kind of properties you want to have, namely this kind of natural behavior under rescaling, then the natural choice for these weights are so-called low-pass filters from wavelet theories. And that has also been exploited by other people in the context of tensor networks and the mirror. But you can also make other choices. But these are kind of nice because these wavelet filters also keep the locality. So if you think about an observable at the core scale localized at a point, then this has basically a localization region that is of the size of the lattice spacing. And if you use these wavelet filters and decompose, then from the perspective of the continuum, this localization region doesn't really increase much. So you stay local. Okay, and for the thing I discussed in the beginning, we are also interested in time evolution, of course, not only the kinematics and maybe also symmetries. And as I said, the most interesting part is when we look at these conformal field theories where we don't have an intrinsic scale. So to this end, let me just briefly remind you how these conformal symmetries are implemented in such a setting. So if you come from the field theory perspective, you think of them as the Fourier modes of the energy momentum tensor if you decompose it chirally. So you take your energy momentum tensor, and this essentially generates local coordinate transformations. Then in a setting like the transverse field Ising model, you can do a chiral decomposition. So the left and right moving parts. This thing, and if you take the Fourier transform of these generators, then these are the local conformal generators, or they form the so-called Virasoro algebra. And there's been a proposal by Ku and Salor already from the 90s how to approximate these objects in a discrete setting. So they have an explicit formula. I think you can also find this in a paper by Vidal and Ashley. And the idea is now that okay, these are kind of approximate versions, lattice versions of your Virasoro algebra, the generators of conformal symmetries. And well, how do you want to think about approximating them? Well, you do this by basically saying, okay, I look at the generator at a certain core scale, and then I use my scaling maps that move to a finer scale and map this up a few scales and then compare it to the discretization there. And then on suitable low energy vectors, because and in field theory is in a sense the low energy effective field theory of a lattice model, you expect that this the difference between these two things goes to zero. And that's how you can get a handle on this approximation error. Okay, so and then well the essentially last technical slide is that we have this kind of main approximation result in these free field pre-Fermion free boson settings, which we kind of think as a meta theorem that also should hold in more general, namely that we exactly get something like this object that we were looking for in the beginning. So if we take an arbitrary observational scale m, which is finer, which is smaller than the scale at which we are actually doing our lattice construction, then we get a precisely controlled error in these cases that depends on this observation scale, on the simulation scale n, and on the time interval we want to look at. And specific cases, I mean, it can also depend on the precise structure of the observables. But so, for example, if you think about these free boson, free fermion models, then natural observables you can write are like polynomials in the annihilation creation operators, and essentially the number or the degree of the polynomial would then also enter this approximation, or the square degree. And so, for example, what we find if we do this for, say, for concreteness for this transverse field Ising chain is that this approximation error scales basically like the inverse square power of the size of the system. So this S would be the size of the system. So if, let's say, you have scale n, then you basically have 2 to the n in 1D lattice sites. And this approximation error scales like 1 over the 2n squared. Okay, and well, this approximation error is kind of decided by the regularity of this low-pass filter you use this method. But this regularity of the low-pass filter is also tied to the size of the observational scale of the observable. So in a sense, you're not completely free to choose that. So you could improve the convergence rate here above 2, but then you're paying like with a larger observable, so you anyway have to go to larger latitudes then to make that visible. And in these models, you can also do like, if you do a naive simulation of these models by basically pretending that you want to simulate these lattice models on a quantum computer and use some standard techniques to get a handle on that, like ground state preparation algorithms for these fixed models and certain Quadracato approximations of the dynamics. Then you can do a gate counting and try to understand how the complexity of these simulations would behave. And there we basically find this delta to the -3/2 behavior when delta is the accuracy we want to achieve. And maybe as a final remark, like if you're interested in like how these conformal generators, for example, in the Ising transverse field Ising model are approximated in certain low-lying states, like single particle states, then get already quite a good approximation if you're doing this only with a few hundred qubits, so which might already be in range. Okay. That's
Sorry, I think you couldn't hear us.
no, I couldn't hear.
Clapping and everything.
Okay, thanks. moment I can't hear anything. I'm sorry, I can't understand you. Yeah, I mean, it's very faint now. I don't know why, because before I could understand you quite well, but now it's... Yeah, no. I mean, can you still hear me? I don't know.
Yes.
Yes, okay, now it's better. For some reason.
Can you briefly comment on how this feature scale, observation scale, is how it relates to the observables and so on, this abstract population?
Well, I mean, that's kind of a model-specific question. So I can kind of answer that for the setting of these free bosonic or fermionic theories or perturbations thereof. So there, it's essential. I mean, there the idea is that this low-pass filter you use to define these RG channels is essentially something like a discretization of a certain test function for the field which your would-be continuum field is smeared with, and so basically the length of this low-pass filter. So let's say here in this picture here. So the length of the low-pass filter is how many coefficients you have here. So that means how far it spreads out when you move from one scale to the other. Now you have to think of that, of course, when you move from one scale to the other, then the new lattice spacing is like, let's say, half of the one before. So you get a kind of geometric progression in terms of how long this wavelength, how long this wavelet filter is, and how your rescaling factor between the different lattices is, and this decides how far spread out the observable is in the continuum.
Thank you. Then thank you again. We have to move on to the next.
Sure. And thanks again for the talk.
Thanks. See you.
Okay, so while Matthias gets his microphone ready, let me introduce him. So it's a pleasure to welcome Matthias Kleinmann, who just recently moved to Münster.
Yeah, I can just put it here.
And recently started a group on foundations of quantum theory, I think. And yeah, I'm very much looking forward to the talk. And I think you can start. Thank you.
Thank you very much for the kind introduction, and thank you very much for inviting me. Yes, I started a new group. There's still one PhD position open, so I'm trying to, where? Here. The pink line. This is why yes, so there's, and I'm working on foundations, but this is actually even practical. There's also a stick, right? So you see, this is something I still did in Siegen. You see here, well, my co-workers, this is Chao Guyen, Gilberto Telemachi Colocozzi, Carmen Diaz-Padros, and Ottfried Güne. So this is Chao and Ottfried are also quantum information guys, like I would also categorize myself as that. And Gilberto and Carmen are high energy physics people. So it's really a collaboration between these two things. What I'm speaking about is basically the paper where they claim to have seen entanglement in top and anti-top pairs. And we are from quantum information and foundations, and we were interested what happened there actually. What you see here is the momentum distribution of the top anti-top pairs, and you see here how the entanglement is basically distributed in the same kind of momentum plane. I will explain this in a second. And you see there's different types of entanglement, and you have to distinguish accordingly what you do. So
In principle, what is cut off in the top? Operational quantum theory. I want to say there's a different language between quantum information and high energy physics, and the language difference is quite large. So that was a problem in the beginning in our project, and we had to really understand what are we talking about. So there will be one slide about quantum information, which I guess most of the people here in the room and maybe also online are most familiar with. So the main idea in our world is that we have quantum systems, and quantum systems have a quantum state. And this makes sense because our quantum systems have a carrier like an ion, and we look at the electronic states of the ion. We have the ion trapped, so it's somewhere. We can manipulate the electronic state, so we can actually change the state, and so we can meaningfully speed out the state. Then we can perform measurements. These measurements are usually, let's stick for ions, you can do a fluorescence measurement. So that's something that you do to the system, and then you get information back. You can even before perform a unitary transformation, and then perform different measurements. We have probabilities for the measurement outcomes, which is given by Born's rule. And you see these illustrations of how we think about this. In particle physics, it's very different. They think about this like an input-output process, or you have an initial configuration and a final configuration, and between these two you have transition amplitudes or scattering amplitudes. And you compute them using quantum mechanics, but you don't really have this notion of a state all in between. So you just compute transition probabilities or cross-sections, and the most confusion is what is actually an observable. I still don't fully understand what is an observable in high energy physics, but I think it's everything that can be computed from experimental data. For us in quantum information, it's specific. An observable is a measurement. In high energy physics, I mean, it's also this kind of thing, but they are much more general. And when they ask, give me an observable, and I give them a pure VM, they are generally unhappy. They don't, this is not what they want. Okay. And particles appear in the cross sections. And if we speak about what we will speak about in a second, the spin of a top and anti-top, we have to be clear that this is somehow something that a concept that we introduced into the scattering process to divide it into two parts. But in principle, they would only speak about cross-sections, and that there's a spin in between is an artificial concept. We look here in particular at CERN experiments, and this is the work that triggered us. So that's a Nature paper. I learned that in high energy physics, Nature papers are not the best, but in our field they are. And they have entanglement, and they have here some entanglement marker. And entanglement marker, for those who are from quantum information, is the same as a witness. Just that it has not to be negative, but there's a different threshold, so it has to be, I don't remember, maybe smaller than -1/3 or so. Anyway, so they see here some entanglement by having this marker more negative or negative enough. And we want to understand what actually happened here and whether we can help or whether there's anything we can contribute with our methods to the high energy physics community. So first, what happened? So in principle, what they do is they, LHC, you might know, they just collide protons. And when they collide protons, they get all kinds of things out of it. And one of the things they see are top-anti-top pairs. Top-anti-top, I will speak about in a second. These are two of the quarks, or one of the quark with the antiparticle. And they have spin 1/2. And the theoretical prediction is that the spin 1/2 of this pair is entangled. So the top-anti-top spin pair is entangled. And there's an exact prediction how it should look like. And then they can check whether it's, they can use an entanglement mark in order to measure entanglement in this pair. For me, the question was, what does it mean to be entangled? There's a relatively large discussion in the field. So in high energy physics, what does it mean for having even a quantum state here? Can you sensibly talk about a quantum state? What did they actually measure? So how does this measurement go? How do we measure the spin of a top, which is a quark, which cannot live alone, and so on? Can we use our methods to somehow improve the data analysis in high energy physics? And can we even suggest new things? That's more or less the program. So let's start into these specifics of the top-anti-top production. So what happens, they collide protons, and then somehow top-anti-top pairs appear. That can happen in many different ways. I don't understand these diagrams, but this is what the colleagues gave to me, and so he showed this in the plot, that in the talk, and it makes sense. So that the meaning is that, well, you have gluons, and they can have gluons colliding, and they produce top-anti-top pair, or quark-anti-quark pairs. They have different probabilities to actually happen depending on the energy of the beam. The interesting part for us is that each of these processes, and there's more maybe, produces a pair, and they have a certain spin state afterwards. And the production channel is just, it's just stochastic, which of them is actually happening, and you cannot discriminate the production channel, at least not with the data that they have available in CERN. So in the end, what you end up with is just a mixture of different spin states, but it happens that this mixture is actually entangled. And so it makes sense to actually verify that you have entanglement there. And you can find a paper, and there's actually really the spin state just written down in our language, so that's quite understandable. Okay, now the caveat, there was this talk about relativistic contextuality. I was not there. Who was the speaker? Sorry, I didn't attend, so because I was a little bit late. But I think the idea here is very similar to what I have also seen in your paper. And this is well known. So entanglement is a quantity that is not relativistically covariant, but we are speaking here about relativistic particles. It's high energy physics. Some of the top-anti-top pairs are very close to the speed of light. So we have to talk a little bit about entanglement here. So what happens in principle is that if you perform a boost of a system in a different direction than the system is moving, and the system has an orientation, so the system is moving that direction, it has an orientation, and you make a boost in this direction, then of course the momentum changes, but also the system gets a rotation. And that's called a Wigner rotation. This is no problem for entanglement in principle, because this is done locally to each of the states, or to each of the subsystems. You have two systems, top, anti-top. You make a common boost of both systems, or even different boosts. It doesn't change, it changes the rotation here, but it doesn't change the entanglement content, because this is a product unitary. The problem happens if you have a mixture of momenta. So if you have different momenta of the, you have mixture, your state contains a mixture of different momenta or states with different momenta. Then you get this decomposition here. How do I do this? You have the decomposition in this form, but now you have the transformation which changes these states, and eventually you can convince yourself that sometimes you can make the state entangled out of a product state, or you can make, or out of a separable state, or you can make a separable state entangled. Yeah. So basically, entanglement is not a covariant property. In the situation of the top-anti-top pair, this is not so bad. You just have to be aware this is a problem. That it's the case. You just have to choose one reference frame and then talk about entanglement in this reference frame. And a natural reference frame that you choose here is maybe the proton beam frame, or just a center of mass system of the top-anti-top pair. Right. Now we come to this plot from the beginning. This is the more advanced version. So what we have here is, first let's try to understand how to read this plot here. We have the proton-antiproton beam, the proton-proton beam, and we produce a top-anti-top pair, and then we get basically the angle theta, which is just the angle with the pipe. Of course, we have cylindrical symmetry, and we have a velocity beta, which is the velocity of the top-anti-top pair. And this is what we plot here. So here we have theta, here we have the velocity beta, and now you see how likely is it to have a state with a certain momentum configuration. And you see that low velocities are quite unlikely, and you see that somehow high angles are more likely. Okay. Here you see how entangled is the state in the prediction by Affek, depending on the momentum. And you see there's a strong dependence on the momentum. And the unfortunate thing is that the most likely states, which are roughly here and here, are the ones which are not entangled. Right? And also actually these states here have different entanglement than these states here. Now for practical reasons, what these experiments, the first experiments have done is actually look for entanglement here in this region at low velocities. So there's very little of them, but they have very high entanglement, and this has other experimental advantages to look there. Okay. So the problems in the analysis are now the following. First, you have this distribution of the momenta, which means that none of the two anti-top pairs do have the same momentum configuration. They are sampled from a continuous distribution, so each experimental data point where you maybe somehow measure the spin of the top and anti-top pair, we have to talk about this, has a different momentum, so you have no means to reconstruct the density operator for a given momentum. It's just not possible. Then you have two technical problems. The first one is you cannot really be sure that if you say that a certain data point is a top anti-top pair, that this is actually the case. You have to identify them from all the kind of things that you detect in the Alice or the CMS detector, and that might be a misidentification. So you might say this event is the top, but actually it was something else. And this is like 20% or so of the data is misidentified. And then there's another oddity. It's actually the top quarks. They decay very fast because they're very heavy. And that means that actually they decay before they really have well, the decay width basically goes to the energy, and that means that actually the equation p squared equals m squares in the relativistic setting is not exactly satisfied, but you have a width there. So if you now transform to the rest frame, or you first transform to the center of mass system, later have to transform to the rest frame for technical reasons, you're transforming to a reference frame which is not well defined because you have an uncertainty in the momentum. We don't care about this, but this is one of the things that I don't fully understand how to really make sense of this. Okay, so now, because we don't have access to individual momenta here, we have only access to data which is sampled from this momenta here, we can at best have actually access to momentum averaged observables like this here. Yeah. So we can only sample, that we can try to measure this one here if we have an observable, and we could measure it depending on the momentum, then we can maybe get access to this guy here, but we will always sample from the momentum. And now it's the question, how do we actually compute this? And that brings the question, what are spin measurements in high energy physics? Okay, so in principle, if you want to measure an observable, you have two ways to do it. Either you measure it directly, right? Or you measure something else and then you compute the value of the observable. So typically you have some kind of, in quantum information, you would use a tomographically complete measurement, and then you can just reconstruct the observable from this data by just using a decomposition of the observable into your measurement observables. Okay. Now, in high energy physics, you don't have a way to really specify what measurement you do. I mean, in the end, what you measure are more or less the momenta and the energy and the momenta directions of the decay products, and everything before that is actually just something that happens to the system. Yeah, what nature does to the system. So if you want to measure the spin of a top, you have to rely on something that the system naturally does. In this case, what you can actually use is as the top decays into well, a lepton and a neutrino and a bottom quark, and that the direction of the decay of the lepton is related to the direction of the spin of the top. At the beginning, this sounds very strange. Why should the decay direction depend on the spin? But you can convince yourself that because of CP violation, this actually has to be the case. Actually, this calculation can be done by a quantum information guy. This is not high energy physics. Okay, in quantum, if you look in the high energy physics literature, you find the following formulas. Basically, like you have a state, they choose a Bloch vector more or less, and then you see that they write down the cross section, and this is the data that you observe. So this is the observed direction of the decayed lepton. Yeah, it's just a unit vector on the sphere. And then they say the cross-section is given by this here, and the parameters of the state appear in the cross-section. If you translate this now to quantum information, that just means you have a uniform POVM, or if you want a covariant POVM, which you can write in this form. So these are just the projection onto the spin eigenvalues with direction u, and then the outcome m for the spin plus 1.5 and minus 1/2 for spin 1/2. And these alpha m's are the constants which determine what physical process you actually have in a decay process. So how the decay process works, if you have maximal parity violation, then this has to be 1 and 0 for spin 1/2. Okay. How much time do I have? 10 minutes? 5 minutes?
10 minutes.
Okay. Okay, so now we translated somehow the spin measurement to quantum information. And now we start to use our things, right? So far, we just somehow try to make connection between the languages, try to understand what is going on. And now we try to do something that maybe the high energy physics people don't know yet because it's rather new. And the thing that we thought of that might be useful is the concept of classical shadows, which was more or less introduced in 2020. And then there was a paper in 2022 explaining the mathematical background. The basic idea of a classical shadow is that it associates an operator to each measurement outcome. So I have, in this case, the measurement outcome is just the direction of the decayed lepton, or of the decay product. And now I can associate an operator to that. And the trick is now that the mean value of this operator is a density operator. If you want, this is basically the inverse of the POVM. And the POVM is a mapping from the direction to the operators, and this is in some sense the inverse to that. Okay. This can be computed. I skipped the slide here. It's just technical. It's just computing the inverse. It's a little bit of tricky. You have to introduce rotational symmetry, and then a lot of actually Wigner-D symbols and Clebsch-Gordon coefficients, and then you can compute this explicitly. So it's not difficult. It's just tedious. Anyway, so once you have given this operator here, then you can this really helps you to compute this momentum averaged expectation values, because in practice we want in principle to compute this type of thing here. So we want to compute an average over an observable, which might depend on the momentum, but we don't have access to rho of p, because we only have access to individual samples for each momentum. So the trick why we can now do this is because we can actually use this operator here in this way here to just write this expectation value as a mean value over the distribution of the momentum and the decay direction and some function that we can compute from this classical shadow. And this is the green thing is the thing from which we sample. So the experiment gives us samples of P and U distributed according to H. And this function A we can just compute. And so computing this average here is just taking the mean value of A. And this is also very friendly if you want to compute error intervals. Okay, so this is the first result that we have. So what we now did is, so the original analysis is just using one witness for the data, and they have to actually post-select the data to be in the regime of very low momenta, because otherwise the witness would not be valid for this. I mean, it would be valid, but it would not be optimized for the specific state that you have. Now that we are able to evaluate momentum-dependent observables, we can actually optimize the witness for each momentum. We have a state that is predicted. We can find an optimal witness for this, and we can each time just evaluate the optimal witness. What we do here is we simulate data using Monte Carlo simulator for simulating the production of the TT bar pairs. And then we just evaluate this as if we would have a real experiment. And you see, so this is an entanglement witness, so negative means entangled. The arrow bars, because we have so many samples, are basically just vanishing. And you see that you can now verify entanglement across the whole region, which was not possible directly without this method. Here's the first result. The second result is, so people, when they see our paper, they say nice. And then the second question is, what is the new observable? And this is the problem I told you in the very beginning, that I don't know what I mean when they ask me what observable do you mean. I try to make them happy with this answer here. As unfortunately a little bit technical, but I have still 10 minutes, so no, 5 minutes. It's only 2 minutes. So this is something that we have experience in quantum optics to be actually really useful. The problem is I can't really tell you why. It's just an experience that this is a very good way to test your experiments. So in quantum optics, you want more or less to know whether you made some kind of, not mistake, but whether you have a misunderstanding of your experiment. So maybe you have some measurements, you make a spin measurement, or you make a polarization measurement, and there might be some things which go wrong you're not aware of. And then you evaluate, say, an entanglement witness, you say it was entangled, but you're not even sure whether the measurements are actually correct. Now this method here, which we now translate to the high energy physics setting, is something that we have applied to many experiments in quantum optics. And most of the experiments we looked at, we could find that they actually have problems in their understanding of the measurement apparatus, to the extent that the problem with the understanding of the measurement apparatus is larger than the verification of the entanglement. So the statistical, so if they want to report entanglement, they should first report somehow quantum mechanics is wrong, because more or less what they prove is that quantum mechanics is wrong before they report I have entanglement, because the statistical significance is higher. Of course, quantum mechanics is not wrong, they just have not a full understanding of the experiment. And this idea we want to transport to high energy physics. We know this is a little bit of an hostile approach, because you say maybe you make a mistake, but it might also be new physics. So the idea is that we try to design general tests which test whether the underlying model, in particular of the measurement apparatus, which in this case is just a decay of the top, is actually valid, or whether we find something that is inconsistent and would require a modification of the model. Okay, this is a long speech before I explain what is here. The idea is very simple. You can basically test whether your data is compatible with a positive semi-definite density operator. So where the reconstructed state is positive definite. The idea is to take just any functional here, which evaluates to be positive under the assumption that the density operator is positive. You can optimize this depending on what kind of expectations you have, that you have some deviations in your data. This test, so basically tests positivity of the density operator. This test, in our experience, is good but not very strong to really detect mistakes in the experiment. Because it's a positivity condition, and if you have noise, you tend to be more positive. So it tries to push you inside of the state space, and therefore it's less likely to actually see a violation. Essentially, what you test here is really the measurement model F here. And you can do another test, which is basically testing the dimensionality of your state. So you can ask, wouldn't it be better to use a high-dimensional quantum system to describe your system? Or to describe your data. So do higher dimensions give you a more accurate fit? And the way you test this is to test basically whether the things that should be zero if you have a spin 1/2 system, which in this case are the spherical harmonics with L larger than 1. They should all have expectation value 0 for this direction of the decayed leptons. And you can just check whether this is 0. And because it's equal to 0, this is usually a very strong test. It means the more data you take, the harder it gets to get equal 0. So it's very, very difficult to achieve this in experiments. Side story, we did this test with the Monte Carlo generators, and they failed. So the Monte Carlo generators failed the actual predictions from quantum mechanics. In the end, it turned out that we used, at least the manufacturers of the generators claims that we used them wrongly and we should use them differently. And once we fixed that, actually it was consistent, but at least we could detect that we didn't use them correctly. Anyway, this is a short teaser how such an evaluation would look like. What you see here is we evaluate the spherical harmonics on the, in this case, Monte Carlo generated data. We have two spin 1/2. This is why this is a matrix. This here is until L equals 1, so this is okay. Everything in here is okay. Actually, it turns out that the state that you have here is just diagonal in the spherical harmonics, but we don't care. But importantly, everything outside of this box should be 0, and this is actually, you can make statistical tests. This is consistent with the assumption this is equal to 0. Okay, so that's more or less what I wanted to say. So basically, the message is you can use methods from quantum information theory to improve the data analysis, and you can also use this to actually suggest possibly new observables, even observables that qualify for high energy physics experimentalists as observables, and now we need to motivate them to do the experiments. Thank you for your attention.
Yeah, thanks a lot for the very nice talk. Do we have questions? Yes.
Can these tools be used to validate an experiment? Like, we need to take specific data from an experiment to verify that our experiment is working correctly? Or can we do this data as a data analysis on the data that we already have?
Before you answer, let me repeat the question for the online audience, maybe. So if I understood correctly, the question is whether you can use these methods directly on your measurement data that you already have, or whether you have to produce additional measurement data. Okay.
Yes. So so now the trick is you use it on the already existing data. So if you did, for example, entanglement witness, and you verified entanglement, you can just use the same data, and then there's certain linear relations which they have to satisfy, and you can just check. So this is what we did in these old times, like 10 years ago. We just asked people, you have the nice PRL, please give me your data, and we check whether it's consistent. Yeah, and that can be scary or not, depending on how confident you are in your experiment.
Thank you.
Okay. More questions? Martin?
So what are really the observables they measure? Like, or what is the data that you get? Is like one infocomplete observable, or do they measure several spin directions?
So
let me repeat this.
Sorry.
Yeah. So the question was, what is the data that they actually measure? Is it just one informationally complete measurement or something else?
Yeah, that's a very So when I teach quantum information, I bring always the uniform measurement as an example, which is nice for exercises but completely pointless. But no, this is actually what they measure. So they measure the uniform measurement. You understand this formula? You look very critical. Okay, then this is so this here is a projector. This is clear. Okay, one of the coefficients is there's only two coefficients because S is 1/2. One of them is 0. One of them is 1. So there's only one of them. This is the spin projector so you have spin observable direction in direction u, and then m plus or plus 1/2 or minus 1/2 are just the eigenvalues of the spin. So that's just a uniform measurement, a different way to write this.
But you need to measure this for at least two different u's to get any non-trivial data.
No, this is a POVM. You know the concept of POVMs? No, sorry. This is of u. This is of a continuous variable.
Oh, okay. Yeah,
sorry. Sorry. Yes, so exactly. So this is the only measurement they have. There's the one measurement, but luckily it's informationally complete. So the only thing is a little bit ugly to evaluate. But so the interesting, this was also my question, like, what is the data they get? And the data that they have at a certain level, I mean, there's many levels of data evaluation, and it's very complicated supposedly, but one level they have more or less is they really have the direction of the decayed lepton and the momentum of the top, which they have reconstructed from other things. So they have these two data for both the top and the antitop, and so it's just 4 momenta basically you get. Each of them have 4 components, so this is the data set, and then you have just 10 to the 7 entries of those, and then you can start evaluating the data.
Okay, thank you. I think we have to move on, so let's thank the speaker again.
Yeah.
So the next talk will not be a scientific talk, but will be a talk about career development, which hopefully shows soon. Maybe wiggle again. Tested before, it used to work.
It says at least, or it does something like, yeah, I am connected, but then it's not. Okay, we already tested it, it worked.
It should work again, right?
There's no signal.
Which doesn't make any sense. It is moving.
Something's changing.
But still no signal?
No, it just blinked.
Do you have to press a button? There we go.
Now it's
So
working.
our
You need the
speakers are
microphone?
Larissa Braun and Jana Lee Steenblock. And yeah, please go ahead, hand over the microphone, just a second.
Okay. Yeah. So I hope everyone can hear us. And we are now going to the career development part. So after your master's, PhD, probably even early career stage of your postdoc, you ask yourself, what's next? What career options are actually out there? How do people end up in jobs using their degrees? And how are they using their degrees? So there are different questions, and our goal today is not to give you the one perfect answer, because you all are individuals on your own path with different wishes and options, and unfortunately also not with the same equal opportunities, but that's probably a part for another discussion. But one thing we'd like to say right from the beginning is this: careers are rarely straight lines. Most people don't follow a carefully chosen path, and from their degree they're going to their dream job. Instead, careers often develop step by step. New opportunities come up, interests change, priorities shift, and many of us find ourselves asking the same question again and again and once more: where do I actually want to go from here? So, introducing ourselves. Before we talk about general career path, we talk about our career path. We
Your name?
are both working in the quantum ecosystem. Every day we collaborate with researchers, students, and industry partners, and many other people in this quantum technology realm. My name is Jana Lee.
And I'm Larissa.
And so I am now working for a cluster of excellence in the management there, and my focus is equal opportunities and anti-discrimination. I have been in clusters before, like managed a research school, and also brought the master study program Quantum Engineering into life and coordinated that the last years. And
yeah, I'm Larissa. I'm now working in the cluster management of QVLSI Labs, where we're focusing on bringing quantum technologies from the lab, from the research into the application. So there's a lot of contact with industries and companies.
yes, so before we go on, we have a little poll for you that you can enter through the QR code or through vote.ac.
So now is the time to get all your smartphones out there, scan this code.
And then you are asked for the ID. That is actually my name, Jana, with double N, minus Lee.Steenblock, with double E.
And if you now start the poll.
Yes, so poll is started, and the question is, what is our background? What did we actually study? Where are we coming from educationally?
Right. If you press on vote, you can just
give your wildest guesses. You can enter 2 or 3 guesses,
yes,
if you like.
Is it not working, or is anyone?
So you have to press vote, and then you have to press send after you typed something in.
Can you repeat the question?
So, yeah, what is our backgrounds?
Like
basically, what did we study?
Yeah.
Educational background, basically, yeah. Now that you know what we are doing, mentioning some quantum stuff.
You might ask yourself, why are we actually standing here? Ooh, we have some answers already. Teachers, masters, yes, I guess masters is kind of right.
Masters,
yes.
yeah.
We have quantum computation, computer science, yes.
Physics PhD
student. Not bad, not bad.
Okay, probably wait for 2 more answers. 2 more. Physics, public relations.
So I guess there's something like physics.
Yeah.
There's something like we did kind of study a master. Something with quantum, something with computing.
So, math masters, okay, physics, yes. So I will close the poll now. And we are having a look into this. So actually, my career started with a master's in philosophy and neuroscience. And straight from that, I got from Magdeburg to Hanover and started working at the Cluster of Excellence in Physics. I worked for Phoenix D and managed at a research school, also had some equal opportunity stuff going on, and managed the study program quantum engineering. I had to learn a lot of new things about a new field, but I think it worked out quite well, and now I'm doing this research management. So for you?
For me, I started with chemistry, so master's was right. I did my bachelor and master's studies in chemistry. Then I also started my PhD in chemistry, but then I changed the universities and also the institutes. So then I did my PhD in physics, which is also right. Some of you guessed it. On foam films, so soap bubbles was actually the field I studied. I did my PhD on. And then after my PhD, I looked for a job and found one in the cluster management now of quantum technology. So a completely different kind of field inside the physics. We also brought to you the career path of a third person from our ecosystem. She actually studied electrical engineering, then did a PhD in physics on ion traps, then went into working in the industry, in the automotive industry for around 5 to 6 years, and thought actually that's not what she really likes. And then she goes, afterwards she goes into a local startup here in Hanover, Braunschweig, and now she's working in the engineering of the QPU on ion-based quantum computings. So there you already see you can go to the industry, then go back, change a little bit the field, being more close to your studying or more far away to the field of studying.
Yes. So after you got to know something about us, we want to hear how you feel about your career plans right now, basically. So please choose the option that describes best where you are in terms of planning your career right now.
Should be on the same page.
Yeah. Vote is not yet started, but here are the options.
The options are: 1, I already know exactly what kind of job I want. Option B, I have changed my mind at least once. Option C, I think academia is my only option. D, I have no idea what comes after my degree. And E, I have considered leaving the field I'm in.
So yeah, we experienced this blinking out and in. I don't know why. Okay, so we have some answers, very different ones. I think a lot of you are choosing, I have no idea what comes after my degree. So, yes, blinks in again, awesome. Okay. And it blinks out again. So always if someone enters an answer. But then I just closed the poll, hoping it comes back in.
Yes, there it is. Wonderful.
So, yeah. So as you can see, there are different stages of your career plans, probably. And there is, of course, no wrong or right answer. Some of you have already clear plans, and probably some of you really don't have any plans yet going on. And I think that is also a message we'd like to take away today. It's that uncertainty that is normal throughout this whole career development process. So this question mark remains, unfortunately, or probably it's also kind of exciting what comes next. So yes, talking about career path. We have always this conversation about academia or industry. I think that's a really common question that you ask yourself. But in reality, that is probably a bit misleading because it's not an either or decision. You can go back and forth, as we already have seen. And also, you don't, okay, academia, yes, but you don't really lose the scientific part of it, probably. So instead, it is probably helpful to think in more or less an ecosystem. So there are careers that stay closely connected to research. Others are focusing on translating the research into applications, supporting innovation, shaping policy, making laws, or by bringing the technology to the society. So you can end up in product management, in technical sales, or also consulting. So the degree doesn't point just one destination, it just opens the doors for different kind of things. Next question for you. You still should be logged in. If not, you can get back there easily. The question is, what did your master or PhD teach you? What's the first thing that comes to your mind?
That's good. I see people thinking and some people are already typing.
Resilience.
Problem solving. Hard work, yes.
Okay, so we already have here a lot of like skills that you develop throughout this thing. So almost, I think, no answer is, okay, there is a quantum physics answer. Because probably the first thing that is also like written in your contract or something, or that you have in mind when you're doing the PhD is probably, okay, I'm doing stuff like quantum mechanics, optics, programming, experimental methods, data analysis, stuff like that. And those are, of course, absolutely true. You are learning those stuff and you gain knowledge in this. But to complete your degree, you have to manage stuff. You have to manage long-term projects, solve problems that didn't have obvious solutions at first, work independently, collaborate with others, build resilience, communicate complex ideas to probably also people who are not in your field, deal with setbacks, stuff like that. So that is all skills, and you already see, okay, yes, I have those, awesome. And this is also the stuff that helps you later on to switch like careers. So.
You're closing the poll?
Yeah, closing the poll and switching. So here you see this again, knowledge becomes more and more specific during your studies, during your PhD, and you gain scientific experience, more and more knowledge. But here's the reality, finding a job matches rarely what exactly you did in the specific field of your PhD, for example. So even in academia, the postdoc position that you become next is probably a bit different from what you have done in your PhD. So if you move to industry, that even gets taken away further more steps. So probably you have not just the knowledge available, you are more having the skills that that brought you there, that you are using in industry, and learn again new knowledge that is specific to the job. So what travels with you? Your competencies and the skills you learn on the way. It's important that you don't forget to sell the other stuff except for your scientific knowledge and to highlight those. Yes.
Yes. Also, I really like that also some of them we just have here, we thought about, you also mentioned, for example, problem solving. I think this is a skill which is very important.
So probably if you go on now, you often ask yourself, what is my field of expertise? But always ask also, what can I do because of the way I learned this expertise? Like you already also mentioned. Okay, let's have a look on the academic career path. So if we have a path there, if this is laid out, the main goal still remains a professorship. So you can apply for a professorship several years after you completed your PhD, when you are a postdoc, and once you established your own research profile. The path there, however, isn't a single track. They range from traditional habilitation through leading junior research groups or holding a junior professorship, tenure track professorships. But what these paths have in common, you can also interchange in these paths, probably you switch these career paths at some point. But you always secure external funding, you publish your own papers, you teach, and of course you network with the community, and probably still best, go abroad for a while and do all this in another country. So here is one also very practical tip. If you are looking for academic positions, often they are not just lined up on a homepage. They also highly push you to contact them. So always try to do like write a group that you are interested in the field. Hi, I want to do my PhD here, or I want to do my postdoc here. For most of the time, postdoc positions are not just advertised. They are often more than they are advertised.
So don't be shy. Just tell the people that you want to have you think about a postdoc, you want to have a postdoc position. Is there anything available? Because as Jana-Lee said, they are sometimes not so advertised, but more you get to, you know the people, you ask directly for that.
Yes. And probably another point that you see here on the left side is that you can get permanent positions or not so permanent positions, but still next to the classical academic career path, research management is becoming an increasingly available path. It's a very diverse field, so there are different tasks that are asked for, like public relations, like establishing partnerships, expanding networks, transfer technologies, doing equal opportunities, stuff like that, working on concepts and strategies. And also for that, you need the different skills we already talked about. So these kind of skills can be really varying throughout the task that you can do with the degree that you hold in physics, for example. So, and then we come to another question before we move on to further career path. A quick reality check, basically. The question is, which of these statements do you agree with?
So now is the time to get the smartphone back in your hands. We have a couple of statements where you can agree with. We have A, successful scientific careers means staying in academia. B, companies mostly hire for technical knowledge. C, a PhD only prepares you for research. D, changing field is a disadvantage. And E, networking matters. And here you can actually, I think you can
choose different.
Yeah. So you can agree with more than just one statement here.
So there are already a few people saying networking matters, and I would highly agree, networking matters, yes. Make sure you build that network go to conferences, be also the person who probably gets in contact over a paper or something with a different group from a different university. Okay, and then there are also people saying a successful scientific career means staying in academia. Probably, yes, you could say that, but you could also have like kind of a scientific path outside of academia, in other research institutions or even in industry. But yeah, I think the most scientific work that you are doing will be in academia.
I think all of us are agreeing that actually companies do not hire mostly for technical knowledge. That I guess is true.
So yes, you should have some technical knowledge, of course, but the skills that we showed earlier are more important because often you are trained on the point there again. But background knowledge always helps, of course. And changing fields is a disadvantage. There's also a person that shows that one. It can be, but I would highly say that it is not true. If you are following the one path that leads to professorship, probably yes, but even then, if you come back from industry, it's also something people want to see. So if there's a change of fields, even if I change from philosophy to something else, it is possible. It is not like a thing that can't be done. If you're willing to learn new stuff, but probably the curiosity is in the room. So yes. Okay, with that, I would like to close the poll and hand this one over to you.
Yes. And right, now we come to the, let's say, non-academia career path. So to start with that, let's start with some numbers from a study here. 10 years after getting a PhD, 4 out of 5 PhD students are actually working in a non-academia position. This can be a very huge variety of positions, for example, working in a private company, but also it is working in hospitals or doctor offices or in the other public positions. To mention this kind of study was doing also having medicine in the field, so that's why there are a lot of hospitals. Now this arises, of course, some pressuring questions for some of you in the room here. For example, which job suits me? How do I find out which jobs suits me? How do I prepare for it? And how do I find out what I already bring for this job? So we talked about the skills and competences you already have, which of them are useful, which not. And also, how do I build contact into the non-university working world? Because so far, probably, you are more in the university world, so there you have some contacts. And at this point, we told you at the beginning, we of course are not able to answer all these questions individually for all of you. However, we are able to give you some advice on how to answer that. And the first one, I will guess, it's a learning process. So answering these questions, understanding job positionings, and understanding what are your strengths and what are your competences, it really takes time. And you will probably not answer these questions at one time, and then they are answered for forever. But a couple of steps or years later, you will have to answer these questions again. Which is also nice because then you are able to change your career. A few very concrete points we can give you are there are self-assessment and competency and transfer tools online you can use. Also, every university has some kind of consulting where you can go and ask for help. If it is like workshops on how to find your own competences, if it's a mentoring program, these are provided by the universities, and if you are unsure about this, you are really welcome to use them. And also for us, it's an ongoing learning process. What exactly are our careers? So it's really nothing that you answered once for all. And also for the last question, how to build contacts into the industry. There you can look for local ecosystems or networks which might help you. And on the local ecosystem here in Lower Saxony, we will come in a few slides to that. Another path of career is actually taking your science into business and founding your own startup, your own company. If you're interested in this path, at each university actually has some infrastructure to help you there. Here I think for Hanover, it's these business startups. So there are people who really help you also with a lot of the IP regulation you have when you have studied here in this university, how it is with the use of patents. There, of course, are some rules, and these are the experts for each university to answer all your questions there. Also here, when you want to start your own business, it's helpful to have some contacts into the industry, and there also a local ecosystem might help you. And now let's come to the local ecosystem of Lower Saxony, our Quantum Valley Lower Saxony, which brings together the university, the research with the private sector, so the companies, and together we are building an innovation ecosystem around quantum technology here in Lower Saxony. Our Quantum Valley Lower Saxony has a network of many partners. You see here their logos. There are academia partners, there are local startups, but also international companies, and they are all working together to bring quantum technology into real-world applications. We are organizing events for young talents, so to help you build your own network and to bring you into contact. For example, we have our Quantum Job Afternoon. The next one will be probably in November in this year, where we invite you to meet companies here in this region who are actually looking for people to hire them. But also we run initiatives like the QVLS Winter School or Women in QT to really help you build your own network. If you're thinking about building your own startup, QVLS offers dedicated help and support you all the way. For example, from just the spin-out guidance, so when is the right time to really build your own company, but also to help you with funding advice to see what kind of grant is important at which state of your company, also to network access and to get the connections with partners, but also with first customers. And we also have some own lab and infrastructure for you. Yes, for the infrastructure, we offer actually fully equipped labs in Braunschweig, so 350 square meters of deep tech infrastructure. They are mostly set up for optical experiments, but also we have a clean room tent, a magnetic shielding, dark fiber connection to the PTB, and of course some general workspace. And these labs are available both for startups so that they can build their own products, but also for technology transfer project, more general. If you're interested in these, you can of course contact us, or if you have any questions about our local ecosystem, you can contact us and ask us.
So we are getting to the end, and there we have a last question. So we have talked now about different career paths within and beyond academia, and also about the question, how do I actually find my own path? Yeah, it's a journey. We'd like to hear from you what would help you to find your career path actually. So think about what you need at that stage. Would you need more information? What kind of information would you need? More experience, more conversations, or probably something completely different? That is up to you. Just enter some stuff that comes to your mind, if stuff comes to your mind. Did I open the poll? Yeah.
Yes, you opened the poll.
Yay!
We always love more funding.
So we would love to provide that. We are always working on that by actually writing proposals, but yes. Equal opportunities, yes, also a very important point. what I'm working on, but please support always. More travel grants for PhD students. Yeah, that's probably also an important point for building that abroad connections, conference connections and stuff. Networking. So money is an important thing. Euroscience. Hire me. Yeah, what skills do you have?
I really like some of them. I want to talk about with people who are in the job to get to know what is going on in this job. Really, a good point.
And the networking events with industries, and probably the quantum job afternoon that was mentioned is some kind of
opportunity
for that opportunity.
Yeah, because there are really people from the industry where you just can go on and have a chat with them.
Yeah.
And really ask, what are you looking for, and also how is your own path to that position at the moment.
So if you are in Hannover or Braunschweig, this is probably an option, or in Niedersachsen in general, but yes.
But I've also seen you're looking for open position.
Yeah, so that's also an important point. Because we're now closing that, and we actually have our open positions. So if you now scan this QR code, you will find open position both on the academia, from the academia institute of our ecosystem, but also from our industry partners. So what they have, what kind of jobs, what they are looking at, you will find it there. Yes. So what we hope you take away is that finding a career path is not discovering the perfect answer early on. You will develop the answers and probably also develop some more questions. And it's about exploring, gathering information, talking to people, also really important. Talk to your peers. Probably you are at the same career stage, but it is really helpful to talk to each other to find out what skills do I have, what skills do you have. So this is also something you can do. Probably talk also with people from other fields in STEM, but talk to other people. Also, if you don't have like a mentor, or if your supervisor for your PhD is not doing the mentoring job like you would like it to be, there's probably also always someone in your group or in the group next to your lab where there are postdoc positions or people who are highly motivated to give you some feedback, to mentor you, or to just share their experiences. Look out for them. And then you gradually find out what fits your interests, strengths, and goals. And often the next steps becomes clearer by taking the first step. That is really important. And not by having the entire path planned out already. So I think there is some time left for a few questions if you have some. We would like to hear them. Otherwise, we are still here.
Yeah, also in the
for the coffee break. And we answer as best as possible, of course, yeah, in our range of possibilities, but yeah.
Can you comment on the policy of the university regarding patents? Like, if someone has a patent idea, who puts the money to get patents?
So I don't know exactly how to. Oh yeah. Oh sorry. Yes. So how is the policy here at the university for patents? Who is putting them into place, or is just overlooking them basically? So I unfortunately cannot like give you a question like this is how it works at the university. But there are people at the university who are experts in patent law and also patents for the university. I think at the LH website you really find the answers to that really quickly, hopefully. I don't know if you already looked that up, so probably this answer is like, yeah, okay, it didn't help me, but there are. Okay, but then we can find out. That's not a problem. I know that there is at least one person handling patent laws here at the university, so they should know. But I have to look up the name and stuff, so I cannot answer that right now. Ah, you know, okay. Awesome. Always a person who knows something. Okay, other questions? Not yet? Also fine? Yeah.
So you're mentioning this career path in management of academics. I think it's very interesting, but I wonder where there's many positions. It seems to me much rarer than professorships.
Probably the permanent ones, yes, unfortunately, but there are always coming more and more cluster-like or Sonderforschungsbereiche and stuff like that, and they all need to be managed somehow. So we see a slight increase in those positions, but yes, they are still rare because academic is not a field where positions pop up randomly because funding. Yes.
Yeah. And also, as you said, they are mostly not permanent.
Yeah.
So that's really like if you have a cluster funding for over, I don't know, 5 years or something, then of course the position is for managing the research of that cluster for 5 years. And then you are working on getting the next funding.
So I don't know about you, I don't have a permanent position. No. So, but I have a 7-year position, what is actually quite good, but it's a cluster of excellence, what has this project timeline of 7 years. Yeah, I'm lucky. Woo.
Better than my 3 years.
Are there any resources for PhD students and postdocs to dealing with the stress of living long-term on short-term positions? Because it seems it has some side effects on some people.
Yeah.
Could you repeat the question?
Yeah, so the question was if there is like support in, okay, you're always having short-term positions and that probably has some effects of your mental health and stuff like that, when I did understand the question right. And the university here has a mechanism that works for that. So we have the psychological, therapeutical consultation, I think is the translation of that. And they are actually directly for those topics, like how am I managing having these kind of restrictions in my career and future struggles and stuff like that. Also, that it's too much pressure going on right now. And I would think that other universities have that as well. Of course, there's also always the graduate academy where people can help with consultation. And for example, the Equal Opportunities Office, yes, that is not only for like women, but also like really supporting you in your struggles. And they're also helping you with mental health stuff, or they at least know to whom they redirect, or they can organize stuff like a coaching or whatever you need in that kind of situation. They are really, really into helping you. Therefore, there are these institutions like Graduate Academy, Equal Opportunities Offices. Also, international offices are really, they are sitting really helpful people, and also this psychological, therapeutical consultations. Yes.
No more current questions. Let's give a warm thank you.
Thank you.
We have a break now for half an hour.
Do you want the mic back?
So welcome back. We start with the afternoon session or late afternoon session. Our first speaker is Martin Plávala from the University of Hannover, and he's speaking about quantum essence of gravity, I would say. Go ahead.
Okay, thanks. So this is based on one of my most recent papers, and the question is about what we can tell about gravity. So this is the experiment that we would like to do that was proposed in 2017. And in this experiment, we have two interferometers. But now, don't get afraid. An interferometer is this thing, that's the first one, and that's the second one. And what's going on here is that here at this point, we do something to a particle. Think of a Sterngerlach, for example, where you put it into a spatial superposition of going down one path and down the other path. So time goes from top to the bottom. And then this particle follows two different paths in superposition, and this one follows two different paths in superposition. So we have two massive particles in superposition of which path basis, or which path just means, is it here or is it here? And also we want them to interact only via gravity. And here's the interesting idea from 2017 from these proposals by Bose et al. And Marleto and Vedral, is that if the interaction would be due to the interchange of gravitons, and if gravitons would be classical systems, then because of the local operation and classical communication result from quantum information, the classical gravitons would not be able to entangle those two interferometers. So if we actually measure entanglement here because of gravity, that means that gravitons cannot be classical, and hence we need to quantize gravity as well. So this is aiming to answer whether gravity is quantum or not. Well, this is a nice idea. There are just a few problems. The first one is that the relativistic locality, in other words, what it means here and now in quantum field theory, is strictly different from the subsystem locality, which is the local operations in quantum information. And actually, Marios Christodoulou from Vienna is working on this. They had a recent paper in Quantum about this, and I highly recommend reading it because it's very interesting. Another problem with this argumentation is that LOCC does not really apply to off-shell particles, because as you know, in quantum field theory, we have on-shell particles, which satisfy energy conservation, and then off-shell particles, and well, LOCC was never really developed for off-shell particles, so that's a bit of a hiccup. Another problem is that you can also say that, well, I have two interferometers here, and so probably their interaction should be described by some quantum theory or some version of quantum theory, but this must have well-defined classical limit. And by classical limit, I just mean that this must lead to a theory in which objects fall down in And already this classical limit of the dynamics is sufficient to give you entanglement. This is a result we did with Marta Marchese, but also Matthias Kleinmann and Stefan Imrichter a few years ago. And so, I mean, the exact implications of this experiment are hotly debated. The current status of the debate is something like this. So there are several people claiming that classical gravity, of course, cannot entangle two interferometers, and then there's several people saying that, of course, it can. And there used to be paper almost every day on arXiv about this, then every week. Now I think we are to something like 2 a month, or maybe 1 a month. So it's calming down a little bit, but with no conclusion, I would say. But here's something more important. I don't really care about this debate. I don't want to be part of this debate. My interest is something different. My interest is that actually deciding whether there's entanglement or not is not a gravity problem. This is a quantum information problem. This is a problem of generation and detection of entanglement. This is what quantum information people do. This is what I know how to do. And this is the problem that I will address using quantum information methods. Because if you know if something is entangled, you don't go ask the gravity people, you ask the quantum information people. That's what I'm going to do here. And so, but before we can actually talk about that, we have to actually look about what we have, what we would like to have, and how to reconcile, you know, the dreams and the reality. So what we have are single matter wave interferometers. So now this looks a little bit technical, but compared to the next two talks, this is still, I would say, like riding a bike with these small side wheels. But what's going on here is that we have just one matter wave interferometer. That means that we take a massive particle, say something charged, and we split it to follow one of two paths. So again, think of a Stern-Gerlach when you like split the path of the particle based on a spin and magnetic field. Then you let it fall a little bit, or you let it time evolve a little bit, like separate it, and then you have to bring them back together. And you have to bring them back together to measure them, because you need to reconcile the two paths to have them interfere and to get, like, you know, outcome of your measurement. The red things that you have around here are just classical masses. And so time goes from top to bottom again. And these classical masses, they just follow a single path, which means that they just stand there, or they just like free fall around the interferometer. And this is possible to do. People are doing this. People are doing this like free buildings down the line. We'll hear more down the street. We'll hear more about that in the next two talks. But people are doing this with single atoms, which weigh something like 10 to the minus 25 kilograms, give or take. But still, this is interesting because we showed recently that you can test this. You can use this to test the Schrödinger equation beyond the classical limit. So you're just not going to be testing the classical limit in which objects fall down in gravity, but you can test the Schrödinger equation, or whether Schrödinger equation is valid for gravity beyond this limit, you know, which is quite interesting experiment. But also, one thing that took me several months to realize and completely clarify the quantum information picture for me here is this. This is just a qubit. Because this L, the left path, and this R, the right path, you can say that these are like two orthogonal states of a qubit. So this is just a system that's spanned by two, well, almost orthogonal states. So in practice, they're like so almost orthogonal that we can just say that they're orthogonal. And that's just a qubit. And that's pretty cool because there's a lot of results in quantum information about qubits. And we can use some of them here. And actually, then even when you think about this transformation, what they do here, you can say that they prepare something like a computational state. Just doing this is applying Hadamard when you split it into two paths. And here, where you recombine, that's another Hadamard. And then measuring computational basis. And that's like a diagrammatic approach to what the interferometer would be actually doing. So this is what we would want to do, the gravity-mediated entanglement. We would want to have two interferometers side by side, and actually so close together that they interact via gravity, but not so close that they interact via other interactions. So they have to be close, but not too close, or not overlapping. And actually, the thing that we don't know here is the time evolution, or that's the thing that we want to find out, or that's the important thing to look at. And there's few requirements that I want to have here. The first one is that the time evolution is linear. But actually, if you are worried about nonlinear time evolutions in gravity, then together with Ruben, the second speaker, we have a paper about how to rule out nonlinear modifications of quantum theory with contextuality. And the second assumption is that the time evolution does not produce negative probabilities, because you cannot really observe negative probabilities in lab, which means that the time evolution as a linear map is either completely positive or at least positive map. And positive is completely enough for what I'm going to do. And there's also one big problem. If you want to have non-trivial gravitational interaction, you have to have enough mass in these two systems, which also means that they have to be heavy enough. So we need something like 10 to the minus 14 kilograms, which should be compared to the 10 to the minus 25 of what we have now. So it's just mere 11 orders of magnitude, not much, right? So, but now, this is how I want to think about these two experiments. In these two experiments, we have preparations, transformations, and measurements. And this is a very quantum information, like almost quantum computing way of looking at it. But I think about it as an operational framework, because somehow my understanding here comes from general probabilistic theories, so from GPTs. And we have to ask, like, what are the preparations and what are the measurements? Well, we know that the preparations, even if we assume that we don't know what the preparations are, we know that they will happen with lasers and magnetic fields, so with electromagnetic quantum theory. And I have a good rule. If you want to do gravity experiments and if you want to investigate quantum gravity, don't doubt quantum electromagnetic theory. So here we are going to assume that quantum electromagnetic theory works as expected, and this will just produce a density matrix. Same with the measurement. I don't even have to know what it is, but I know it's going to be done with some cameras and electromagnetic stuff again. So I know this is going to be some POVM. I don't even have to know which one, but it will be some POVM. And in principle, it can be any preparation and any measurement, which means that the only thing that we don't know is this transformation, and that's the only unknown term that we have to look at, and that's the unknown term that we'll be looking at most of the time. Because now we can use this insight to actually reduce the number of interferometers instead of 2 to 1, you know, so this is like budget saving. EU has to love this because you just build one interferometer and then make it to do the work of 2. It's like what we do with postdocs in teaching, like you hire one postdoc and make it do work of 2 professors when teaching. So this is how we can do it. You take one interferometer and have it in superposition, and then you take other interferometer and not put it into superposition, just make it follow one path, okay? In principle, we can do this, at least as a Gedanken experiment. We still have this unknown time evolution here that we don't know what it is, but if we would be able to do these experiments, we can measure some partial data about this time evolution, where here psi is arbitrary wave function, so that's arbitrary state of this interferometer, and this LL is like formally a position eigenstate, so that just means that this interferometer is localized within one path. Now the trick is that a localized interferometer is not an interferometer, it's just something that's localized in space. So like I am one arm of a localized interferometer, you know, because I'm just doing this, I just have my position here. So this means that we can get some partial data about time evolution with just one interferometer and something around it, if we pretend that the something around it is one arm of a localized interferometer, right? We can, of course, then just have it follow the other arm, also localized, not in superposition, and still claim that, yeah, this is just exactly this data about the time evolution. And now here comes the big step, is that we can bound the rest of the terms of the time evolution using semi-definite programming. In other words, using this partial data, and using the fact that the time evolution is positive, we can simply bound what the rest of the terms can do, because otherwise it would violate the positivity of the time evolution. So we are doing an experiment we don't want, and then we somehow are able to bound the outcomes of the experiment that we would want to do. But there's still one problem, and that's the mass scale. And here we would like to do this with masses that are 10 to the minus 14, but we have 10 to the minus 25, so we have to deal with this. And dealing with this requires an explicit assumption, but I'm not going to hide it. I'm going to just put it here like in black and white. Yeah, so this is the problem. These are the interferometers that we have that we are building, and these are the ones that we would want. So, you know, the 11 orders of magnitude difference. And the assumption is going to be like this. The time evolution of the gravity of the both interferometers depends only on the product of the masses and not on the masses separately. It's not telling you whether this time evolution is entangling or not. It's not telling you whether it's quantum or not. It's just telling you that the interaction depends on the product of the masses. This is not something I invented. This is essentially every interaction that you can find in a textbook, because Newtonian interaction, it's product of the masses divided by distance, right? Electromagnetic interaction, product of the charges divided by distance. Whenever you look at an interaction, there's product of the interaction charges, in our case masses. So yes, this is an explicit assumption, but this is an assumption that you can find almost anywhere done in quiet. And what this buys us is that if you want to do experiments with, well, I said 10 to the minus 14, but also 10 to the minus 12 would work. It's just 2 orders of magnitude heavier. Then 10 to the minus 12 times 10 to the minus 12 is 10 to the minus 24, which is the same as 10 to the minus 25 times 10. So what this means is that if you would want to do experiment with 2 mesoscopic particles of the mass of 10 to the minus 12, you can also do experiment with a particle with mass 10 to the minus 25 and a 10 kilogram chunk of tungsten. And then if this assumption holds, then the same result you would get if you would use these 2 particles, right? So this is the plan. Just do the experiment with an atom and some chunk of tungsten, argue using this assumption that the same would happen for 2 mesoscopic masses, and then use the previous reduction from 2 to 1 interferometers to say something about whether there would be or would not be entanglement. Yeah, so now I can move to the result. And the results are as follows. So we just take a single interferometer experiment, and we test the Schrödinger equation for all the localized microscopic systems in the gravitational field of a nearby mass. So you just take one atom, split it into spatial superposition, have some masses around so that you test the Schrödinger equation, and just get all of this data that you can. Now, the observed data, I cannot tell you what the observed data would be because I cannot see the future, but I have a very good guess. The observed data should look something like this. So the non-trivial time evolution, or the non-trivial terms, should correspond to when the delocalized particle is like, when you're looking at the off-diagonal elements of the density matrix of the delocalized particle, you know, so this is the ket-bra of like, this is the off-diagonal density matrix. And of course, you have to have the other particle localized because we have only one interferometer in reality. And then the realistic thing to assume is that you'll have some phase shift, and moreover, we somehow expect phase shift to be very close to or exactly given by Schrödinger equation. So this is nothing else than just the Hamiltonian, and the Hamiltonian here is just equal to the potential because we are in the Eikonal approximation. So this is the corresponding unitary operation, and then we might have some decoherence here. And now we would want to know this decoherence, but the experimentalists are not going to measure the decoherence exactly. They're at best going to give us something like the bottom point of the error bar. Because what we will aim to do is that we will aim to measure the decoherence due to gravity as closely as possible, and there's two options. So we'll get some error bar, and either the error bar includes 1 or it does not include 1. If it does not include 1, where 1 here would be unitary time evolution, then we have effectively experimentally ruled out Schrödinger equation. I don't really know what happens with gravity, but I know that my job prospects would significantly increase. If the error bar includes 1, then we have not ruled out Schrödinger equation, which is what I would expect would happen, but we will still get some kind of lower end of the error bar, which will be an upper bound on the decoherence, because it's like the more decoherence you have, the lower this number is. So like numerically lower bound is upper bound on the actual decoherence in the system. So from the experiment, we'll aim to get this kind of lower bound. And now we plug everything into an SDP. So now we can check whether for given obtained lower bound, there is some time evolution that does not generate gravity-mediated entanglement. So here the not is very important. This is the word doing all of the work, because now using semi-definite programming, I can actually iterate through all of the possible positive time evolutions such that they are consistent with this to be observed data or this expected data, and check whether all of them do generate entanglement or whether there is at least one that does not generate entanglement. Okay? And then if the assumption is valid, then this applies to the mesoscopic masses as well, and then we have indirect proof of gravity-mediated entanglement. And here's the numbers, because of course I just ran the SDPs. The SDPs are actually quite simple. It's not as simple as a homework from a Quantum Information 101 lecture, but it's something you would expect a master student to do in 1 month maybe, or 1 to 2 months. So what's going on here is that on the x-axis we have this lambda naught. This is the lower end of the error bar that we would get from the experiment, right? So this is exactly this number here. This is what we expect from the experiment to observe. On the horizontal axis, you have the minimum eigenvalue. But let me explain first of all what's here. Here, this is the plus state, and the plus state is like the equal superpositions, like left plus right, So it's just the plus state that we know from quantum information. It's what you get when you apply Hadamard to 0. This plus tensor plus is the usual input state of the gravity-mediated entanglement experiment, because we just assume that both interferometers are in superposition at the same time, and this would be the exact superposition. We apply the time evolution that would make the interferometers interact, and then we do a partial transpose. Because one interferometer is a qubit, 2 interferometers are 2 qubits, and if you want to know whether a state of 2 qubits is entangled, just use PPT, or positivity of partial transpose. So we just apply partial transpose, and then we compute the minimum eigenvalue of that, or we bound the minimum eigenvalue of that. And that means that whenever this line is negative, that means, so for example, at this point, that means for all possible time evolutions phi of t that are consistent with this number of lambda naught, this is the highest possible minimum eigenvalue that you can get. So whenever this number is negative, that means that you will always get an entanglement in the corresponding GME experiment. And then we can see that the critical value here is something like 0.9995, at which point you are very confidently negative, and you can conclude that if you would prove that, if you would bound the decoherence to this level, so 9995, that you can conclude that yes, gravity must create entanglement. We don't know what it would do to 2 interacting interferometers, but we are quite sure it will create entanglement. And with that, I have some conclusions. So the first one is that actually the indirect experimental proofs of gravity-mediated entanglements are on the horizon, and in the next 2 talks we'll hear more about atom interferometry and how the experiments are going. But the more important thing is that for a very long time, people have been saying that we cannot make progress on quantum gravity because you don't have any experiments. We don't know what will happen, you know. And physics without experiments is not like fish without a bicycle. It's like a fish without gills. But soon we will have experiments, and actually it's not going to be the experiment that's going to be the bottleneck. It's going to be the theory, because soon we might be able to say that, yeah, we expect gravity-mediated entanglement to exist, but now we need to do more theory to know what it means. Also, some future steps that are probably going to happen soon is that actually one should look more closely at this interaction, and then one can probably reduce the numbers or improve the numbers a lot, which of course is very important for doing the experiment, but also what we're working on is to adapt this to realistic experimental proposals. Yeah, and with that, I'd like to thank you for your attention.
Thank you, Martin, for this talk. Are there questions? So I've seen this talk 3 times, so I know many questions, so please.
Thanks, Martin. It was very clear. I think it's a very nice way of phrasing the experiment overall. So just to understand your assumptions, if you put them together, right, the linearity together with the idea that the evolution only depends on the product of the masses, and you actually apply this to, say, someone performs experiment with the mass of 10 to the minus 25 and the cube of tungsten or something like this. Indirectly, then, your assumptions would imply that it's possible to get this 10 kilograms of tungsten in a superposition of positions, right? No. You're not assuming that when you use linearity of your phi, because how come? Because you're assuming that you're using the 10 to the minus 25 and 10 to the 1 and then you're using linearity on that, right?
Yes.
So it's so how come you're not assuming how come this is not a consequence of your 2 assumptions?
So you assume that such a state would be mathematically well defined, but that doesn't mean you have to be able to create it.
Okay, fair. Do you think it's a reasonable assumption? A reasonable consequence. Let's put it this way.
I would say so. This assumption, the mass product assumption, this one. I find it very interesting because, first of all, when I start talking to someone, I say, like, this is my assumption, everyone's like, yeah, okay, good. I mean, why are you even telling me this? It's like, if your assumption is that gravity exists. And then I start drawing the conclusions, and then people are like, start squirming in their seats, you know, a little bit like, yeah, okay, maybe we should look at this further. And one of the important things of this assumption is that it forbids self-decoherence due to gravity. Because if, you know, self-decoherence means that your system would decohere even if the other mass would be 0. But then the whole interaction would be probably 0, or most likely 0, unless you have mass-independent self-decoherence maybe, or something like that. So in principle, maybe one could conclude from this that the spatial superpositions of like any object should at least be principially possible. Whether we can do them in practice, I don't know, but at least like should not be strictly forbidden by nature, but even that's maybe a little bit open. So one needs to work more on this assumption, what it exactly means.
About quantum gravity at this point, right?
Yeah.
About how, like...
But I mean, so your point is, so we have time for discussion. So actually your point is a little bit that if it's not possible to superpose 1 kilogram or 10 kilogram objects because there's some auto-decoherence or whatever, or because of general relativity, then your experiment would do what? You would see it in your experiment, right? It's part of the thing you can test.
No, you wouldn't, because how would you test whether you can superimpose like 10 kilogram chunk of tungsten?
I mean, you would break this assumption.
If you were able to, but
nah.
That's not what you're trying to do. You're trying to do a different experiment to draw conclusions about what would happen in the 10 to the minus 12.
Yeah. Yeah. So I mean, for example, if you want to drop this assumption, what you just need to do, like there's 2 things. First of all, you should just get one interferometer in this mass range, which is easier than having 2 of them, and just test for its decoherence on its own, like whether you see more decoherence the more you increase the mass. But also you can just, if you want to drop this assumption completely, it still means that you just need to take one of these interferometers and drop the same mass next to it. So But of course,
depends on which scale you want to test it, but yes.
Yeah, no, I mean, then you completely circumvent this assumption if you would have actually interferometer with this mass. But we don't have that, so we have only this one, so then we need the assumption. So then, I mean, one can probably look into how to test this assumption, or whether we can test it, or what are the theories that would violate the assumption, and can we test them, and so on. But yeah, that's future work.
More people having problem with this slide or any other questions? Please, who want? I can repeat.
The coherence and the phasing. Because additional gravity gradient will always lead to additional dephasing in a wave function, but that does not necessarily mean the coherence.
Yeah. So
you have to repeat the question, maybe. Or?
Oh yeah. How do I distinguish between decoherence and dephasing? So the additional gravity gradient is not considered in here because I just somehow assume that the experiment just happens in vacuum of space or in an empty universe. So this would most likely be some kind of extra source of decoherence or dephasing that we just have, and we have to take it into account. So there's two options. Like the first option is to perform essentially process tomography of this channel, which is not so easy because you can send localized things through. You can send stuff in superposition, but you cannot send, or it would be probably quite hard to send stuff with like complex coefficients. So we are more or less constrained to one plane in the Bloch sphere. Although you probably know more about that than I do. But in principle, like I would not only suggest to look at these terms, but I would suggest to like do as much process tomography here as we can, just to be more complete. But also, I have some newer calculations that suggest that expecting time evolution like this is most likely the correct way to look at gravity. Of course, you have then other sources of like other effects that will be happening there, but these ones we hopefully get rid of using differential measurements and so on.
Do we have more questions? So is the experiment that you're suggesting do you use all of the data or all of the things that could be tested? Are you taking, or is there do you think that your data analysis, there could be more constraints you could extract which you did not find yet? Or do you have some kind of assumption that is, or some kind of statement of completeness, like there's not more to be found if you only have this data?
So I think it's work in progress, and I think it could be proved that there is not much more to be found in this regime, unless you start explicitly testing other assumptions. So unless you, for example, because there's like, okay, positivity, we are not taking away, that one must stay, but the linearity of the time evolution, like the Schrödinger-Newton people would maybe object to that. And you can of course find other assumptions, like, I don't know, what if the space is discrete?
Yeah, or there's no infinitesimal, there's no real numbers. Okay, let's thank Martin again. So the next talk is by Michael Werner, and it's more experimental, is this correct?
Halfway.
Halfway on atom interferometry. Please go ahead.
Perfect. Thanks for the introduction. Hi people in the room, hello YouTube. So yes, I'm Michael, and I would like to talk with you about atom interferometers as have been just introduced. And I'm in the group of theory of quantum sensing in the Institute of Quantum Optics, so we are more of the theory department in the experimental department, kind of. And I want to introduce to you atom interferometers more thoroughly and tell you what cool things we can do with them. But first, I would like to introduce to you the concept of interferometry, but I mean, I'm preaching to the choir, talking to physicists, so most people know interferometers from light interferometers, and I should rather use this one, I guess. So light interferometry we all know, for example, from LIGO, the big interferometers that measured gravitational waves, because there we have light, here depicted as a red laser, And we have a beam splitter here that just creates a superposition of my two light fields, and then they traverse space. And for example, in the case for gravitational wave detections, we have a phase shift that is imprinted here just because the baseline or the length of one of the arms is changing with respect to the other. And then we put the light fields back together and we do a light intensity scan, and then we can see fringes. In atom interferometry, light and matter change places. So in an atom interferometer, we have atoms. We prepare them, like millions of them in a cold BEC, but conceptually you can always think of having one atom. And then we apply some light fields that kicks the atom into a superposition of two different states. So you can think of 50% of the atoms get an additional photon kick, such that our atoms are then in a spatial superposition along two different paths in space-time. And they will also encounter some differential phase. And if we overlay them, we can also see some fringes. So in a nutshell, in a light interferometer, we use matter to split and recombine light, whereas in an atom interferometer, we use light to split and recombine matter. And since we are here in a quantum info perspective, I would like to bring this also in the formalism that Martin just proposed. So we can always break any atom interferometer down into 3 steps. We initialize our atoms, for example, cold BECs, and we bring them into a certain motional and electronic states, because these are the 2 degrees of freedom that we can change in an atom interferometer. Then we have the actual interferometry scheme, which consists of free propagation and atom light interactions. Here, for example, we have a beam splitter first that brings our atom into a 50-50 superposition of a 0 h-bar-k motional state, which is from before, and we kick some of the atoms with n h-bar-k, so they get n photon momenta, so that the wave packet splits into 2 wave packets. And here, for example, we also change the internal state. However, this is optional. Then we have a mirror that inverts these 2 kind of paths, and then we recombine them. And in the 3rd step, we detect and extract the phase. So let me start with the state preparation first, but I will keep it short. What do we need for a state preparation? We need an experiment. And Martin just said also that we have a big experiment here. This is the Welfen Castle, which is quite nice, at the Leibniz University. In there is the Institute of Quantum Optics. And if you go through the park, just to the northwest, we are here right now, then you can see the high-tech building. And this is where the big VLBAI, the very long baseline atom interferometer, is located. You can see it on the right. It's roughly 15 meters high, and it does not fit into the building because here we needed to increase the ceiling by roughly 1 meter, so it's here. This is the top. And this is quite cool because in this experiment you have 2 different sources. One is already installed, which is a rubidium source, and there we can trap bosonic rubidium-85 and rubidium-87. And to be installed hopefully soon, there's also an ytterbium source at the top where we can have multiple different ytterbium isotopes. I just named a few here. And we then trap these atoms in a cold BEC. Here just very shortly 2 animations, for example, for single species rubidium, that we trap them and put them into a BEC, or which is more non-trivial, to have dual species, here for the example of rubidium and potassium, in a single trap. And then you can see some non-trivial dynamics of where the atoms actually are in a trap. And there we keep them very, very cold. Then the next step, atom light interactions, beam splitters, and mirrors. I will just give you one example here because there's a plethora of options. And the example I want to show to you is Bragg scattering, which is a 2-photon process where we fully stay in the ground state. As I said, it's optional to change the internal state. And here you can see the energy momentum diagram of an atom, just depicted here as a 2-level system, ground state, excited state. And we have our atom talk to 2 light fields, here depicted in red and blue. And what you can think of here is you have your atom. It absorbs 1 photon from the light field, for example, from the bottom, such that the atom gets a kick upwards. And then there is a stimulated emission into the other light field from above. So the atom emits a photon to the bottom, so the atom gets another kick upwards. So essentially, the atom will gain a momentum h bar kr, where kr is the effective wave vector, which is the sum of these two. And this is how we transfer momentum to the atoms here. Today, we will leave it at this example. There's more and more and more of these interactions, but I want to focus on something else, which today is the detection. So how do we detect fringes, and how do we extract the phase out of a cold atomic cloud? Here we have the experiment. I will just show you how it's done. We have the atoms, we shoot them up, we bring them down again, and then we take a photo. So this is a CCD camera picture of my output port. And if I just change the momentum states, I know where my atoms will be if they have 0 h bar k, and where they will be if they have n h bar k as an output. These are the two output ports of my interferometer. And here you can see this is the picture I get. Then I do a population estimation, which is just a Gaussian fit of this. And then I put this into a population scan. And here you can see there's a phi L that I vary. This is just a phase I apply to the last beam splitter laser. And this is a phase that I can just imprint onto the atoms. And now I can change the phi L and get another shot, another picture. I put it into the population scan. I do this multiple times and then get a curve, because then I can create some population scans here and get this interpolation function. And using some algebra, I can then see and find that this interpolation function here, the population as a function of delta phi, is just given by this cosine. This C here is the contrast, which is ideally 1. If I, loosely speaking, start with 1 million atoms and I end up with 1 million atoms, my contrast is 1. Usually it's lower, but okay. So the experiment measures this population here. And from this, we can invert the formula and get a function for the delta phi. Then there's the theory department. They model the analytical form of the delta phi. So they just solve the Schrödinger equation for the example that I've just shown. One phase shift that is quite popular, and which is, like always, the working horse experiment, gives you a phase shift which is proportional to gkt squared, where g is just local gravitational acceleration, and k is the effective wave vector. And then we can get an estimator. In this very easy case, where the phase is just gkt squared, and we are, for example, interested in small g, we just take the phase divided by kt squared, and we get an estimator for g. Very easy. This is called gravimetry. And this is where I come into play. This is the theory department where we are working on to get these phases. Some of my colleagues are working on the BECs. Some people work on the atom-light interactions to make them more efficient. This is my job. Just to get this out of the way, there's also the possibility to do a differential measurement. For this, you can have two interferometers here and here. And one interferometer can be very noisy because the lasers are very noisy. There's a lot of noise sources that come in. If you have two of them, common noise will drop out because you can just plot the population of the first and the second interferometer like this. Then you get an ellipse. And from the eccentricity of this ellipse, you can get, from the eccentricity of this ellipse, you can then get knowledge about the differential phase between these two interferometers. And from this, you can also deduce doing some algebra, solving the Schrödinger equation again, you can get some information from this delta phi here, from this small delta phi, and reduce all of the common noise, which is very, very cool. One last slide on the theory on this and the detection algorithm before I come to the big, cool problems, which is the phase calculation heavily depends on the interferometer geometry you look at. The one on the left is called the Mach-Zehnder interferometer. It's like the Michelson interferometer. It's the working horse experiment, where you just stay with the lower path in 0 h bar k. You add a few, let's say 1 h bar k to this path. Then the lower path comes up again, and then you measure up here. And then the phase looks something like this, where you have the term I've just shown you, gkt squared, which is the linear gravitational acceleration. There's also a term which measures potential rotations of your axis, which is given here. And if you also have like a gravity gradient in here, like a linear gradient in your gravitational field, it will also pop up here. And there's way, way, way more terms that you can detect. Because of these dependencies, we say that an atom interferometer is a very good quantum sensor that measures inertial forces, so accelerations and rotations. You can, however, also create a rather asymmetric configuration where I just do something to my upper path of the interferometer like this. I kick the upper path up, I kick it down again. Sometimes these geometries are called asymmetric Ramsey-Bordet interferometers, and they have more or less the same phase shift like here, but also some terms that have some recoil dependence. So here we have some h bar k over m. And keep this in mind, this will be very important, because if you ask, what do we actually do with atom interferometers? Why are they so sexy, at least in my opinion? The biggest experiment right now, or one of the biggest experiments, is used to detect and measure the fine structure constant. The two biggest experiment and most accurate experiment for measurements of the alpha come from atom interferometers. And how do they do it? First, we start with the definition of alpha. This is alpha squared, some natural constants, as you might think. Then we have the Rydberg constant, and we can put it in here to rewrite this formula like this. And then there's the most important and very, very good thing you can always do in mathematics is to multiply by a cleverly chosen 1. It's very powerful to do this trick, where we have here the mass of the atom. And then we can rewrite this term to have something like this, which is known to very high precision. Here we just have some natural constants, 4 pi and c. The Rydberg constant is known and measured to a few parts per trillion. And here you have the atomic to electronic mass ratio, which is also known to a few parts per trillion, depending on the atom, coming from spectroscopy. And here we have something that can be measured with atom interferometers, h bar over m. Why do I say a measurement of h bar over m? Of course, since a few years, h bar is set by the SI units, and now we don't measure h bar over m because we only measure 1 over m, but the name stuck. And we can do this because, as I just told you, there are interferometer geometries where this phase shift depends on h bar over m. It's just in there. And the two big experiments right now on the planet are the one in Berkeley and the one at LKB in Paris. Here I just depicted the two interferometer geometries. I just want you to see they are more complicated than the ones I've shown you before. They are very, very complex and complicated experiments. They are very big, and they do this now for a long, long time. This is why they are so good. Just as an example also, you can see here some dashed lines and some solid lines. These are different kinds of atom-light interactions. On the left, for cesium, we have some Bragg transitions that I just showed to you, and in the middle, some Bloch oscillations. On the right, we have also Bloch oscillations and some Raman transitions, so two different kind of laser-atom interactions. But the most important thing is, here you can see the phase, and here you can see 1 over mass of cesium, and here we can see 1 over the mass of rubidium. And this is the thing we want to find out. We measure this phase and get an estimator for h bar over m, or rather 1 over m. And these experiments are now extremely precise, but there is a problem. These are the latest two measurements, and the error bars don't overlap, and they don't overlap with 5.4 sigma. So this is quite an open problem we have right now. And we don't know what is the problem. So this one is the work that I just showed to you from the LKB, which has an accuracy of 81 parts per trillion, which is astonishing. And if you look at the quarter-eta value of alpha, the error bars there are essentially are the error bars from here. And we don't know what is the problem right now. In the middle, here in red, there's a theory prediction, which is essentially quantum field theory calculations of the anomalous G factor of the electron. the G minus 2 essentially, and they need to go to very high orders of Feynman loop corrections. Right now I think they're like 8th order loop corrections, so they are calculating right now, and it's somewhere in the middle between these two measurements. So this is an open problem we are now facing as a community to see what is the problem here, what is causing this inconsistency. But I promised you Einstein. Where does Einstein come into play? I just talked about the very small things. One example for Einstein is the weak equivalence principle. I mean, we all know back then, 1971, wasn't it a good time, where people went to the moon. Hopefully we go back there soon. And there they did this famous experiment of the hammer and the feather and let them fall in vacuum. And we saw that they fall exactly the same. But if you look very, very closely, a hammer and a feather, even in perfect vacuum, won't fall exactly the same, in the sense that they won't have the same trajectory because they have higher order mass moments. The universality of free fall goes into the universality of trajectories, if you want to call it like this, only for point particles. But a hammer and a feather are not point particles. However, atoms more or less are, because they have no charge, they have no mass moments, at least to very high accuracy, and they are identical everywhere. So we would like to do gravimetry with atoms, because I just showed you we can very precisely measure small g. And when we measure small g for 2 atoms, we can, in the end, measure the so-called adverse parameter, which is just this parameter here, dimensionless quantity that tells you how big is the difference between 2 local accelerations. And here are just some milestones. This is a very incomplete list of quantum sensors that did gravimetry. And here always in the color code for rubidium-85, rubidium-87, people did it with strontium, again with rubidium and potassium, again with rubidium. There's a lot of stuff going on here, and they improved over the years. There's also some experiments that brought BCs into space, because I want to do an experiment for hours, right? And compare my Gs over a long, long time and let them fall very long. But my experiment is over when my atoms hit the ground. So I want to go to space. So this is what people also try now. With this, we kind of reach a limit of 10 to the minus 12 right now. It's increasing all the time. However, we are short behind the classical experiments. Like the newest one is the microscope mission that does this weak equivalence tests in orbit with test masses, with macroscopic test masses. They bounded eta to 10 to the minus 15, but we are on it. Then there's also the gravitational wave detection, where Einstein comes into play. Because here you can see, very broadly speaking, the expected gravitational wave detection threshold and the strains that we will be able to measure using the light interferometers that already exist, like LIGO, and the proposed ones like LISA or the Einstein telescope. And there is the highly anticipated mid-frequency gap in here in the decihertz range. And people really want to measure there. But LIGO has a big problem with seismic noise, and LISA also decays here. So what to do? Atom interferometers can possibly help, because here I showed you the curve of a 10-meter interferometer. We will never detect gravitational waves with a 10-meter atom interferometer. 100-meter looks better. 1,000-meter looks even better. And one of my jobs is now to do some realistic simulations of where these curves will actually be, because they won't be like this, because noise will also come in. Seismic noise will also affect atom interferometers. Gravity gradient noise comes into play. Laser phase noise comes into play. There's a lot of reality that will bound these curves, but atom interferometers really have the tendency to detect gravitational waves in this range. How do we do it? Just very briefly, I want to show you the trajectory and the geometry of the atom and the interferometer. Here, once in the lab frame, so we always have, on Earth at least, our parabolas of the atoms. In the freely falling frame, where I just get rid of small g, we can see it like this. we have so-called diamonds, where we open the interferometer and we split the two atomic parts of the wave function, bring them back together, open it up again, bring them back together. And using multiple diamonds and choosing big T correctly, to choose it essentially at half the frequency of the incoming gravitational wave, we can have a resonant buildup of phase that we are then able to detect and measure, which is quite cool. For this, we need to change the internal states. Also, you can see we go from ground state and excited state to excited and ground, and so on and so forth. So this is a very cool experiment, and the first large-scale interferometers of 100 meters are built as we speak. Then also we did some analysis here to include other general relativity effects. My two theory colleagues, Domenico Giulini and Philip Schwartz, here from the ITP, developed a huge Hamiltonian that included all 1/c² effects in a weak gravitational static space-time, which looks like this. We then took this Hamiltonian and applied it to atom interferometers. You can read everything in here, which was also quite interesting. For 10-meter interferometers, we won't be able to detect space-time curvature, but we did the analysis nonetheless. Just a small outlook. With Elina Fuchs, also from the ITP, we do some dark matter detection strategies, because, for example, scalar ultralight dark matter will just mimic itself as a change, a periodic change in the alpha, in the fine structure constant, and I just showed you how to detect and how to measure alpha, so we can also look for changes in alpha, obviously. So as a small summary, atom interferometers are very versatile quantum sensors. We can detect a lot of inertial forces, rotations, accelerations, test the weak equivalence principle, and in the future maybe also detect gravitational waves and dark matter, and we have the most accurate measurements of alpha right now. As Martin also said, there's the gravity-mediated entanglement that we can test. There's also proposals to detect a so-called gravitational Aharonov-Bohm effect, seismological studies, groundwater analysis. All of this I will subsume in, let's say, Earth observation. So atom interferometers are very versatile. So thank you for your attention. Thank you to the sponsors here, the Quantum Frontiers and the AGAPS project. And if you want to download my codes, they are all written in Python. They are all open source, because I think that science should be free and accessible to everybody. And our goal is right now to create a community-owned and open software package for the whole interferometry, because we think this is very important for the ongoing and upcoming field of atom interferometry. So thank you for listening.
Thank you very much. Other questions? There's no, so maybe I ask, so in this large Hamiltonian, what are the important terms? I mean, can you highlight something?
Essentially, the most important stuff is the center of mass Hamiltonian, which you could see here, and there's some 1/c² effects. Usually, something you can see here is something like special relativistic fourth-order kinetic terms. So these come into play quite easily at large scales, because you just have long propagation of atoms. There's also some effects that come in just from the laser fields, because if you have here the light Hamiltonian, which is shifted a bit via the gravitational potential, you need to solve the Maxwell equations, which is quite a pain. But you can do it in a geometric optics approximation. And then you can see that the phase of the light field depends on the height, essentially. But this will only come into play at the very long baseline interferometers, where you have 100 meters that you traverse. But yeah, essentially it's these terms here in the center of mass Hamiltonian that change the trajectory, the atomic trajectory.
And they are uncontroversial, so it's not interesting to measure them directly, or is it also an interesting project?
It will be interesting, but we can't do it with 10 meters. And we only have the 10-meter interferometers next door. And the first atom interferometer that will have 100 meters is probably the MAGES 100 experiment that is built in the US right now. Mm-hmm. And since it's the first of a kind that has 100 meters, it will be, I guess, challenging to directly measure space-time curvature effects, but probably we will measure it in 100-meter-ish experiments.
So I just 2 weeks ago heard somebody speaking about 800-meter interferometers in some years.
Yeah, there's a lot of proposals right now in the world. I mean, China has some proposals. The European Union has some proposals. There's the so-called TVLBI, the Terrestrial Very Long Baseline Atom Interferometer Proto Collaboration. They are looking at different options right now. So there's a lot of effort into building these very, very long baseline atom interferometers, also for gravitational waves and stuff. But these space-time curvature effects could also be detected in there.
And they don't have to be vertical, it can also be horizontal, or how is it?
Yes, there's also the horizontal ones, for example, MIGA in France, which is also a gravitational wave detector, which is is horizontal and goes into 2 directions. It looks more like LIGO in this sense, which is also possible. The one in China, for example, which is proposed, is vertical and horizontal.
Mm-hmm.
Because then you have more access to polarizations of gravitational waves, for example.
Questions from the audience? Yeah.
So how exactly are they proposing to build 800-meter interferometers that are vertical? Because that's like the height of Burj Khalifa, I think.
Yes, I mean, there's a lot of proposals right now, and I don't know what, I mean, there's multiple challenges that come in for these very long atom interferometers. I mean, first of all, laser power. You need a laser that traverses all of these heights. And each laser is essentially a Gaussian in the end. So your laser is going to be very wide in the end, and you don't want this.
No, wait. My first question would be even like, how do you want to get the 800 meters long quite stand upright?
I mean, there's some proposals for like mine shafts, like that are existing right now. There's also, for example, the Gotthard tunnel that has some support shafts. There's support shafts at the CERN right now, which is the ACE proposal. There's the Bowlby mine, the Derby mine in Bowlby in the UK. So there's a lot of existing long tubes, essentially, that people could use. But yeah, 800 meters is very extreme. But people don't want to dig a kilometer of vertical tube in the end. They try to have something which already exists.
Well, more questions? We have maybe time for. I have a very naive question. In the beginning, you showed the 2 species interferometers.
Mm-hmm.
What is the benefit? I didn't fully understand of having 2 species.
This is essentially for the weak equivalence test. So when you want to let 2 atoms fall at exactly the same height, let them fall in the tower, you want to have them start at the exact same height. So you want to put them in the same trap. So you want to prepare your atoms of potassium, ytterbium, rubidium, and then put them in one trap and just turn off the trap to let them fall.
So they can be trapped in the same trap,
yes.
But the lasers are very different to manipulate them, right?
Yes.
Okay.
I mean, it also depends on the atom source and all of this.
But it still improves precision.
Exactly, yeah. You really want them, because otherwise you have a co-location problem. If you have 2 separate traps and you want to really make it in the same trap, and cool them in the same manner, but you also need to know how my atomic cloud looks like if I have 2 species in the same trap, which is very non-trivial.
Okay. Then thank you very much. We go on to the next speaker. But now we have a real experimentalist, no?
Okay, this works. Microphone. This will do.
So the last, I don't have your first name, unfortunately. So
no worries. Guillermo Alejandro Pérez Lobato.
Then it's your name. Thank you. Please go ahead.
You can call me Memo. Hello, everyone. Thank you for being here. Thank you for the invitation. It's a pleasure and an honor to be here tonight and be closing this event. This is a very experimental talk. So this is pretty much a follow-up on Martin from the theoretical side, on Michi, on the Mikael, on the binding glue between experiment and theory worlds. And this is pretty much what we're up to in the very long baseline atom interferometer project and in the VLBAI experiment. So I hope I have made these slides at least somewhat interesting for the theorists, for the quantum information people. That's the hope, but let's see if we manage to. So first, and to begin with, I would like to introduce you to the team and to the experiment. This is the VLBAI team. It's 6 people working mostly on the experiment and 3 PIs. Out of the 6, 5 of us are PhD students, and Joel is our postdoc. And the experiment, it's the very long baseline atom interferometer here in Hanover. It's next door, like 5 minutes walking. And it's a very large interferometer. Atom interferometers, in particular, this one is a gravimeter. It's in vertical configuration. They are typically lab-sized or typically desktop-sized. They're like this kind of machines. And this is a particularly large one. There's only 3 of this size in the world. There's one in Wuhan in China, one in Stanford in the US, and this one here in Europe. There's many more planned, but the existing facilities that are operational and that actually work on a day-to-day basis, only 3 of these. They're also building the one MIGA in France, but they still have a way to go before being fully commissioned and operational. In any case, this is the generalities of the machine. And the science that we are doing, it has many scientific goals and objectives on various different things, from fundamental science to applications, to applied science. So, for example, we have the stick. We can do clock interferometry to measure, for example, gravitational redshift and how does gravitational redshift affect clock interferometer or an interferometer in a with a macroscopic delocalization of the wave function. That is one project. A comparison of the acceleration of 2 atomic species. This is a weak equivalence principle test in the same sense that other people have already done before, the ones that Michi mentioned, such as the people in Stanford did rubidium 85 and 87. Here we want to do a comparison between rubidium and ytterbium. Macroscopic delocalization and superposition of the wave function. This also goes into the side of things of spontaneous localization models or models of spontaneous decoherence. It's most likely, like I can already tell you, it's more likely that on an experimental basis, technical noise sources would come in before we can measure any spontaneous localization, because it's pretty hard to measure spontaneous localization and distinguish it from imperfect vacuum, from imperfections in your experimental imperfections, such as vacuum pressure not being 0. But this is putting bounds on it would be a good place to start. And the project that I am working on, which is putting a small additional tungsten mass near the atoms and measuring the gravitational influence of this small additional mass near the atoms. With this in mind, with this scientific goals and objectives in mind, I would like to tell you a little bit about the machine. We use a BEC. We work with rubidium 87. Maybe I can use this one. We have 2 atomic species, just to make some emphasis on this, rubidium in the bottom and ytterbium in the top. Rubidium is already installed, commissioned, and operational. That's the one that I am working in. Ytterbium is still being developed. It is in prototype phase, not yet ready to commission. Mali and Mario are working on ytterbium, and it's being developed in the CASO, and when it is ready, it will be moved and installed into the baseline, which is here in high-tech. But those are the 2 atomic species that we're working with. In any case, because of the large scale of the experiment and because of also some other reasons, we have technical demands that are not the same as for every other atomic interference experiment or atom interferometer experiment, such as demands on the temperature of the atom cloud. We need a very, very cold cloud of atoms. And this means that we need a very high quality atom source that has very cold atoms as a result. And for this, we use an optical dipole trap, and we use BEC in an optical dipole trap. I'm skipping all of laser cooling. Laser cooling typically has 2 or more stages. We usually begin with near resonant light, with near resonant light, with near resonant photons that cool and trap the atoms to a certain level. And then, in order to achieve a BEC, we need a conservative trap. In this case, we use an optical dipole trap with 1064 nanometer 50 watt lasers. And I'm going to this much experimental and technical detail because of a previous question that was asked in this session, which is whether we can trap and cool the ytterbium and rubidium atoms in the same trap, even though the resonances are different. And the answer is you cannot cool them and trap them with the same resonant or near resonant light, but you can cool them and trap them with the same optical dipole trap lasers. So that would be the answer. The optical dipole trap laser can trap both rubidium and ytterbium in the same trap. You usually need more power for ytterbium because of higher mass and other reasons, but you can use the same optical dipole trap laser to have them both of the kinds of atoms, both the atomic species, co-located in the same trap to an extent. If you're interested, if the audience is interested, we can discuss more about this detail later. In any case, what I want to show you in this slide is that we have an experimental sequence. We can create up to 10 to the 7 atoms with single nanokelvin temperatures. And we can do either a single BEC or we can do many at once for various reasons. We can either launch them both together and measure with many parallel measurements, or launch them sequentially one at a time and manipulate them in various ways. So we can also do that. In any case, this is more about the temperature and the expansion velocity. When you are this cold, it stops making sense to talk about the temperature. It starts making sense to think about how the atom cloud expands, because temperature in the classical Planck sense of the word means equilibrium, and it requires a reference material or a reference system that you are in thermal equilibrium with. And here, the atom cloud is not in thermal contact with anything. It is like so isolated from the rest of the universe that it's just there in the vacuum chamber. So there's no thermal contact to be in equilibrium with a second system. You can have 2 atom clouds in thermal equilibrium with one another, but it's really about temperature first in a sense of phase space density, but we do not need a very high phase space density because that also puts us in other problems, that also gives us other troubles. It's rather that we need very low expansion velocities. We need the atom cloud to have a definite size and to stay that size, to keep that size even though as time goes by that it expands very slowly. And that is what it makes sense to think about and talk about expansion velocity. And the point is we can do matter wave lensing to achieve very low expansion velocities, up to single or near 0 millimeters per second expansion velocities. And our atom cloud sizes are typically 100 micrometers or less than 100 micrometers across. So this is what we do. Now, with this cold atom samples, can you remind me until what time do I have?
I think it's still 20 minutes or something. Yeah, 20 minutes.
Okay, perfect. Then we have enough time to go into all the details. With this cold atom clouds and this cold atom samples, we can use additional lasers to manipulate them, and we can do coherent atom manipulations, such as beam splitters, and launch the atoms. So we can manipulate the center of mass motion of the atom cloud, and we can also coherently split, propagate, and recombine the atom clouds. And with these tools, these laser manipulation tools, we concatenate them together to create our atom interferometers. So we have two laser frequencies coming in from the top, which are reflected on a mirror at the bottom. And this interact with our atom cloud. As Michi just told you, this is a Bragg beam splitter diagram where the atoms begin and end in the same internal energy level state, or in the same internal state, but with different target or ending momentum states. So we only manipulate the momentum state of the atom, not the internal energy level state of the atom. And we can still do this coherently and split the wave function coherently, which is what you see here. It is a two-state system, an effective two-level system, and we can drive Rabi oscillations between these external momentum states. And these Rabi oscillations are what you see here. So when you have a 50-50 probability, 50% probability of measuring the atom or encountering the atom cloud in either one of these two states, then you have a beam splitter. And if you coherently transfer all your atom cloud population to the target state, then you have a mirror pose. And with this, we have the atom optics required and necessary to concatenate them together to create an atom interferometer. And a question that always comes up again is, what do we want an atom interferometer for? What does the atom interferometer do? And what the atom interferometer does is that it's a sensor, and it measures a variety of things. Initially, it measures gravity. So it measures gravitational acceleration, small g, the acceleration due to gravity, or the gravitational acceleration, and the local version, not big G, but small g. And with this, we can have a measurement that has a very high precision, up to, for example, a single nanometer per second squared. This is a lot of significant figures, say beginning with 8, 9, 10, or up to 11 significant figures. It is always a good question to ask, how real is this measurement? What's not only the precision of the measurement, what's the accuracy of the measurements? Does it actually correspond to reality? If you're interested in that, let me know in the questions and we can discuss more about that. In any case, we can do this measurement with the atom interferometer, and this is the scheme of the interferometer that we have, which is a Mach-Zehnder interferometer, where we have our source, our beam splitter, which happens here, our mirrors that happen here in the middle, and a final beam splitter to recombine them, which happens here in the end. And we measure our observable, and this is an experimentalist trying to borrow vocabulary from the local source, the local field of quantum information. Our observable are atom populations, and the difference in population in these output ports is our P, our final measurement. And as you can see here, we have a working atom interferometer, and we have interference fringes, which we can sweep. We can change the position of the fringe that we're observing by chirping the phase of the laser, chirping the phase between these three poses of the laser. We moved the phase of the laser a little bit, and with this we can sweep the position that we are working in. We have achieved measurement of gravity, but we are still working on improving it, on scaling the space-time area that we can measure in order to improve this measurement. Now, coming to what we're doing and what are the prospects of our work, one of the things that we're working on is to measure the propagation phase shift. This is to measure the gravitational influence of an additional test mass, an additional mass near the atoms. And these are tungsten masses, which are 15 to 16 centimeters away from the atoms, outside the vacuum chamber, but close to the atoms. And this will enable us, this allows us to measure a gravitational Hadron bomb effect, where due to the symmetry of the mass distribution around the atoms, the net force of the masses on the atoms is equal to 0 because the acceleration due to these masses is 0, but the potential is non-zero. This means that we may be able to measure a phase shift due to the potential and not due to a mechanical force that is moving the atoms. This is the gravitational equivalent of the Haranov bomb effect. I can see that the audience maybe disagrees, but we can debate about this. Like, this is what we can do with gravity. We can also move these masses and have a dynamic potential, a dynamic gravitational potential near the atoms or around the atoms, which leads us to be able to tune Newtonian noise and measure dephasing due to the gravitational interaction between the masses and the atoms. And in general, to position these masses near the atoms with sub-millimeter accuracy in order to tune the gravitational potential. Now, one thing that I would like to emphasize is that in order for this measurement to be physically interesting, we need the macroscopic delocalization of the wave function, this delta z, the difference in position between the atom clouds, to be greater than the distance between the atoms and the masses, this big R. The R is the distance between the atoms and the masses, which is 15 to 16 centimeters, and the delta z needs to be larger than that. We are still working to improve our matter-wave interactions, our light-matter interactions, in order to increase the macroscopic delocalization of the wave function. We are in a good trajectory to do so, but to be completely transparent and honest with you, we are not there yet. We're still working on it. It's ongoing work to increase this include space-time area by the atom interferometer for this measurement to be real. We envision this to happen near term in experimental terms. This is the implementation of the masses. This is what the masses look like. They are 5 centimeters height. They are 23 millimeters in diameter, and they weigh 400 grams each. And we will put initially 8 of them in these tubes, which are 16 centimeters distance from the center of the baseline and from the atoms. And we can tune their positions, tune their height. We can position the masses with accuracy of plus minus 0.3 millimeters, and we can move them with up to 10 meters per second velocity, which will enable us to co-move the masses together with the atoms following the atomic wave function, like for half the baseline, for up to about 5 meters on the way up and also on the way down. So yeah, we're working on this. And a general statement about the interest of this research is both in fundamental physics but also in applied physics, whether we can distinguish between a change in local acceleration g and a mirror vibration. Say, for instance, with this atom interferometer, this square and the baseline here, the cylinder, represents an atom interferometer, we can measure gravity, but we may also be able to measure spatial or temporal variations in this gravitational acceleration. Temporal variations such as, for example, groundwater. This is what I try to represent here by the groundwater movement or groundwater density changes due to the mass of the water below our feet, and to measure the groundwater level below our feet without having to drill a hole in the ground, having to dig, or a spatial variation with a transportable atom interferometer that can measure in many different places or many sites across a field campaign measurement. And in principle, if we have mirror vibration, if the reference that we're measuring against, it's not stable, we cannot distinguish between mirror vibration or the mirror moving and the local acceleration changing. So we need to do something about this in order to tell these two apart. And this is one of the things that we're also working on, which comes back to how sure that your measurement is actually true, really is. So with this, I would like to conclude that the very long baseline atom interferometer is commissioned and is measuring gravity. We are still working in making this measurement better. and increasing the enclosed space-time area to enhance our measurement and make this measurement better. But we're well on the way to do so. And that atom interferometers can be used as tools and as measurement tools for precision measurement research in areas such as measuring the propagation phase shift due to additional masses near the atoms and near the atom interferometer. With this, I would like to thank again the organizers for having us here and letting us talk about this research that we're doing on an experimental basis, your neighbors next door. Thank you.
Thank you very much. Are there questions? So you proposed at least 2 questions during your talk. One of them is, why do you measure gravity?
Why? What for?
Well, but I mean, whether you really measure gravity or what do you measure there? This was one question you proposed, so I'm asking you, and do you really measure gravity there?
That is a very good question, because it's a matter of the accuracy of the measurement. How sure you are that your measurement is actually real, that it's actually true and corresponds to material reality. And the point here is that by the Einstein equivalence principle, we cannot distinguish between motion of the mirror and motion of the atoms. So we can only measure relative motion between them. The mirror, the dielectric surface of the mirror where the reflection of the light takes place, that's our master inertial reference. This is what we measure gravity against. So in order to measure gravity very accurately, we need to stabilize the mirror. And this is what we have the seismic attenuation system for. So this system that is here, this seismic attenuation system is a system that holds the mirror very steady so that we can ascertain that the acceleration that we're measuring is due to the atoms moving and not due to the mirror vibrating. So this is one of the things that distinguish our facility from other similar or comparable facilities. This is one instrument that we have that other facilities do not have yet, or that they do not have at the moment. It's one of the key components of our facility to have the seismic attenuation system that enables us and allows us to have a better accuracy in our measurement, not only just precision, but accuracy. And this happens because the facilities in Stanford in the US and in Wuhan in China, for absolute gravity or small g measurements, they are limited by seismic noise, by mirror vibration. And this is a device that we have to work around that problem.
Are there more questions? I have a follow-up question to this, but I want to give the audience a chance. So wouldn't it be an option to take other forces than gravity? I mean, gravity is nice, but is mostly very weak. But you could look for, I don't know, some dipole forces, I suppose, or some magnetic forces, and then maybe even calibrate this kind of things. Or are you only checking gravity here?
Yeah, for now, we're interested in measuring gravity exactly because it's one of the harder ones to measure. Everything else, like magnetic field gradients, couple into our measurement as noise. So we can measure it, and we actually have a solenoid around the baseline in order to superimpose an additional external magnetic field to measure that and to measure against as a reference. So we can do that. And one system that I did not talk about, but we also have, is a magnetic shield. The magnetic shield is the black thing that you see here. It's not black in real life, but it's black on the image to have contrast. Everything is metal gray, like everything is metallic, so it all would look the same in an image. The black thing is a magnetic shield that shields our atoms and shields the baseline from mainly the magnetic field of the Earth. So it takes this away so that we are not measuring the magnetic field of the Earth, but we're measuring the atoms falling. So yeah, that also couples, absolutely, definitely also couples into measurement.
Okay. Thank you. I have more questions, but we anyway meet later, so maybe we just do this later. Is there any question from the audience?
I have a question.
Yes.
You said at some point that you chirp a laser. What does it mean?
That's a very good question.
Could you repeat the question or
So
Yes.
what does it mean to chirp a laser?
To change the frequency of the laser. It essentially means to move the frequency that the laser has. And to be honest, what we do is mostly Doppler spectroscopy. We have to match the frequency of the laser to match the velocity of the atoms. And to chirp the laser means to move the frequency of the laser. We usually do this to match the velocity of the atoms, and that's how we take these ranges here, for example. Change the frequency of the laser so that it matches or doesn't match the velocity that the atoms are falling. And then we can see like the relative difference on the laser phase and the atoms' position and velocity. This is also a reason why this experiment is super interesting, because due to the symmetry of the mass distribution, the force would be equal to 0, but the acceleration is also 0. Then this means that if we measure a phase shift or phase shift contribution due to these masses, even when the atoms do not change their external momentum state, their momentum, their velocity, the positions and the velocity with which they are falling, then we have something interesting. Because it's not explained by doing Doppler spectroscopy, it's something else, which will be very interesting to measure. Where does it come from?
Okay. Other further questions? Doesn't seem to be the case. Then thank you again.
Thank you. Thanks to you all.
The organizers have some closing remarks, no?
You first. Okay. So I would like to thank everybody that was here today. Thank to everyone that watched this online or will watch this online. If you're watching this from recording, please like, share, and subscribe. And also I would like to thank Sean and Yasmin. They're PhD students in our group. Then they helped organize everything, carry everything around. So they really helped a lot. And thank to you too. And I hope you all had fun, learned something new today. I definitely did. And we'll maybe see each other at some conference.
Nice. Thank you, Martin.
And thanks to Rick for streaming and making this happen.
No worries, no worries. Thank you. All right, so just to finalize everything for Rio. So this all started in 2023 when I decided to do this for the first time, and I traveled to 5 different places to do something like this. And in every single place, it was a very different experience. It was very nice to see the different kinds of research being done and all this, and people enjoyed it. And then I promised to do this again. So I did this again this year. This time I went to 9 different places: Stockholm, Vienna, Ponferrada, Waterloo, Manchester, Dublin, York, Hangzhou, and now finally I came here to Hanover. I think that this was a great ending to the conference. It was very nice to have, or to the conferences, right? The many conferences. It was very nice to see experiments, theory, from hardcore mathematical quantum field theory to talking about gravity-mediated entanglement, how to probe this with the experiment. So thank you so much for presenting all of this. This was an amazing experience. This is the last local RQI circuit, but it's not over yet. Next week, there's the online edition with people from all over the world, from smaller institutions. They're not really at local hubs or anything like this. So I invite you all to next Friday from 9 a.m. to 4 p.m. We'll be streaming online talks starting from Australia and going all the way to California with different talks around the world. So feel free to go to the YouTube channel and to watch these if you're interested. And so thank you so much for organizing everything. And yeah, thank you. And we are